Humanities and Social Science at NIT Rourkela. He holds a PhD in economics from the Indian Institute of Technology, Kanpur, and has a strong academic background in econometrics, optimization, international trades, and development economics. Professor Mishra has been actively involved in interdisciplinary researches, including projects focused on tribal empowerment, regional industries, and sustainable development. With over 40 research papers published in a reputed journal indexed in SCI, SSCI, Scopus, and APDC, his ongoing work in areas such as energy efficiency, FDI, and urban economic dynamics reflects a meaningful integration of urban theory with real-world urban challenges. In today's session, he will be delivering a hands-on training on structural equation modeling. The session will include step-by-step instruction along with guided assignments. We are delighted to have him with us today. With that, I now hand over the session to Professor Bikash Ranjan Mishra. Over to you, sir.
Okay, thank you. Thank you very much, Padmaja. And thank you very much, Professor Ankur and Professor Suparna ma'am, for giving me this opportunity to share my limited knowledge with this August gathering. So we are already running out of time. So let us start our discussion. So let me first share the screen and then we'll be moving forward. I hope the slides are visible now.
Yes, sir.
Yes, sir.
Okay. So
Excuse me, sir. Sir,
yes.
only a request. Can you please hide the sharing tab below?
Okay.
Coming up on the screen. Thank you, sir.
Okay. Is it okay now?
Yes, sir.
Okay. Thank you. So in the next couple of hours, my objective is to introduce a concept called structural equation modeling. I'm not going into the intermediate stage or the advanced stage of the structural equation modeling. Rather, the approach will be the preliminary one or the introductory part only. So the outline of the presentations will be like this: structural equation modeling, which is better in the acronym known as SEM. I'll give a brief introduction, history about SEM modeling. Then moving further to the features, example, advantages and limitations of the model. Then certain any question? Okay. So moving further to the certain key jargons and the different types of SEM, will be further moving to steps of SEM. Then the second part of the discussion will be with respect to the different data analysis. So broadly, the SEM, as we will be unfolding the discussion, we can get to know that it is a combination of two approaches, two analysis. So one is a confirmatory factor analysis. The second one is known as the path analysis, and the combination of the both will be the overall SEM model or the SEM discussion. So it will be divided into three parts, and as and when we'll be getting time, we'll be going to the STATA software, and maybe it is handed over to all of you in the previous day. And if not, then also not, it doesn't matter, because in the second part of our discussion, in the post-lunch session, two of my PhD students, those who have already joined, I guess, they will be helping you to discuss the same thing, not only in STATA, but also with the help of R. And focus will be more on R, because I'm sure the other 3 days discussions are with respect to the free software discussions. So I'll be telling them to conduct the same data analysis that we are going to do in the first half, or maybe some fresh data in the second half with respect to the R software. And in the first half, I will be using the STATA software to discuss the different tree analysis and a graphical exposure of it, which we call it as a SEM builder in the STATA, with the help of a graph. How do you execute it? That will be the entire subject matter of our next couple of hours. So usual disclaimer: if you have a any question or any clarification required during the period of discussion, then you just ask as and when then only. So that will be useful not only for you, but also to clarify the doubts and then moving forward. So that will be the usual practice that I undertake. But if it is okay to allow for the last, during the last hour of the presentation, any questions and discussion, that is also fine with me. It is completely up to the participants and the audience as they feel, comfortable, they can raise their questions. Is it fine? Should we proceed further?
Yes, sir.
Yes, sir.
Okay. So, starting with a brief history about structural equation modeling, as I have told you that it is basically a combination of factor analysis and path analysis. So, factor analysis has a age old, it has a very large history. It is almost more than 100 years before. And basically, it is started with respect to the social science field like psychology, the Charles Spearman and what you call the Ellen Thorston in the 1904 and 1930, they have developed certain psychometric tests where these factor analysis were very, popularly used. So basically, they proposed a correlation between the test material, mental abilities, which can be have common factor representing ability. So these are broadly with respect to the psychological. Moving further to the path analysis, they use certain kind of a simultaneous equation modeling, and the field of application is genetics and basically the physical sciences, medical sciences, and economics, and later it moves to the sociology field also. So broadly, in the 70s, almost 50 years before, these two methods they are clubbed together and they give rise to a modeling called the structural equation modeling. And the proponents or the main developers of those particular combination of factor plus path analysis, the credit goes to Hauser in 1971 and Jorexkop and Kilsing Willie, they are the prominent figures. And till now, this particular field is in the evolution stage, and there are many other dimensions also need to be
Yes.
added. And it is already added. It is in a what you call a evolution stage till now. Any doubt till now?
No, sir.
I somehow listen some of the voices. So right now I'm not in a position to see the screen. I'll just want to focus on the PPT. So if there is anything, then the moderator please take care of it. Okay. So moving further, that what is an SEM? So SEM, it is basically encompasses a broad arrangement of models from linear regression to measurement models to simultaneous equations. So basically, this is not just an estimation method in particular, rather it is a way of thinking, writing, and estimating a model. So basically, it is a class of statistical technique which allows us to test hypotheses about the relationship among the variables. It may be referred to, or in other words, it is better known as analysis of covariance of structures. SEM fits models using the observed covariances, possibly means, and it encompasses the other statistical methods like correlation, linear regression, and factor analysis. So basically, it is a multivariate technique. I will tell you what is the meaning of multivariate technique shortly, which estimates a system of equations. Variables in these equations may be measured with error. There may be variables in the model that cannot be measured directly. So in that context, there is a concept of latent variable, which is occupying a very prominent role in the SEM model. And these are the certain technical jargons that we'll be going to discuss soon. So broadly, this is the fundamental idea that SEM is nothing but it's a combination of two further approaches called factor analysis and path analysis. So moving to the salient features of this SEM model, it works with multiple related equations simultaneously. So what does it mean? That will be more clearer if you go to the next slide with an example. So what we can see from this example that there are three attributes, or there are three dimensions of health is taken into consideration. One is the physical health, second one is the subjective health, and third one is the functional health. So functional health may be what you call depending on two more variables called y12, y22. Similarly, physical health can be depending on two or more variables. For the sake of simplicity, I reduce it to only two. And similarly, the third dimension called the subjective health, which is the ultimate objective of our discussion, or maybe ultimate objective of our, researcher. So in that case, that particular variable also depends on two more variable. So individually, two factors contribute to each dimensions of the health. And broadly, the physical health is not only going to affect the functional health, but also the subjective health. And subjective health is also influenced by something called the functional health. So in this way, what happens? There is an interrelationship among many variables. So physical health is the most prominent variable, which is affecting functional as well as subjective health. So if you consider it as a variable one, and this is called variable 2, and this is called variable 3. Each variable, they are depending on two respective determinants. It may be 2, it may be more than 2 also, depending on the nature of the objective of the researcher or maybe the theoretical background. The determinants may be more than 2 also. What we are representing over here is a simplistic case, a hypothetical situation, that if suppose y1 and y21 may be any two determinant of physical health, they are defending their physical health conditions. Don't be confused with respect to the direction of the arrow. Rather, what happens over here, it is not physical health which is going to affect the y11, y21. Rather, the approach in the structural equation modeling will be like that. Being in a particular condition of physical health, certain outcomes of y11 and y21 are arising. So that's why the y11 is the, what you call the cause of the physical health. And similarly, y21 is the cause of the physical health. But for example, suppose the blood pressure, high blood pressure, or maybe the diabetic condition, they may be the two determinant factors for affecting the physical health. So in that condition, these are the two indicators as well as these are the two determinant which is going to affect the physical health. If the blood pressure condition is in a balanced portion and same is also the blood sugar level, then accordingly these are the two determinants or indicators which is going to affect physical health. So in the similar manner, the other variables can also be discussed in detail. Anyway, we'll be discussing them in detail in several times in our subsequent lectures hour. So what we are trying to show over here is that individually each variable, they are associated with several series of variable, and then ultimately when the three variables are generated, then these three variables also related each other in terms of the direct effect or maybe in terms of the indirect effect. Direct effect in the sense physical health may directly affect the subjective health, functional health may be directly affecting the subjective health, but physical health may also affect the subjective health via something called functional health. So physical health effect on functional health via A path, and then functional health effect on the subjective health via B path. So corresponding A and B gives rise to something called the total effect of the physical health on the subjective health. So that is the broader idea about the structural equation modeling. So it works with multiple related equations simultaneously. That is why we call it as a simultaneous equation model to a very limited manner, not in a full detailed manner, because simultaneous equation model has its own path also, has its own branches of discussions also. So we are not going into that part of the story. Second thing is that it allows reciprocal relationship, though we have not mentioned any reciprocal relationship over here. So it may happen that subjective health not only affect physical health, not only affect subjective health, maybe vice versa. That means subjective health and physical health may have a feedback relationship. And similarly, also functional health, maybe subjective health has a feedback relationship. So whether there exists a feedback relationship, two-way relationship, X affects Y, Y affects X also, or it may be like this framework where there is no what you call reciprocal relationship. Third thing, ability to model constants as latent variables allows the moderator explicitly capture the unreliability measurement of the model, because certain models, certain measurement things are whether they are reliable or non-reliable, because majority of them are not observable also. So because health component or maybe certain kind of like what called anxiety or maybe certain other type of health factor, psychological factor, Even if in the economic sense, when we say that I derive a lot of utility by consuming a particular commodity, so whether that utility is a what you call quantifiable term, I do not know, because for me a particular commodity's utility may be different, maybe high, maybe low in comparison to you. So in that case, certain variables are there in different spectrums of social sciences, and I'm sure in other urban planning and other disciplines also, which we call it as a latent variable, and they may be reliable, they may not be reliable. So in this way, the SEM model can take into consideration the factors to make them reliable. If there is a test of such thing, then how to do that. So that will be the subject matter of SEM. And as we have seen previously, that it is not only discuss the direct effect, but also the indirect effect or the mediating effect. Like over here, the functional health over here is playing a mediator role or a moderator role, and it is not only affecting the subjective health directly, but also via physical health also it is going to affect. So in this way, there is an indirect effect of physical health on subjective health also, and it compares the performance of a model across multiple populations. So these are the salient features, and with respect to an example, we discussed the SEM model, what is all about. Then moving its advantages or the limitations part. So basically, it's a correction of for measurement error, the reliability estimation. It is more reliable. Complex causal models can be handled in a better manner without going into the deep or detailed complexity analysis over here. So model testings are rigorous. Statistical model, they can be compared with each other. So on the basis of certain parameters, we can say that model A is preferred over B, or B is preferred over C, or something like that. And then it also considers or covers certain things called missing data. If there is some missing data in the total data file, then with the help of this SEM, it can nullify that effect of the missing data. Either it will delete from the database, or with the help of certain imputation mechanism, it will generate certain data, and then on the basis of that data availability, it will go for the interpretation, or it will go for the statistical testing. Then finally, it has certain extensions also. Those extensions that we are highlighting over here, but it is just for the purpose of knowing that what may be the possible extensions, but we are not going to cover them in our discussion. So the extensions of structural equation modeling can be going into the multi-group analysis, measurement equivalence, longitudinal models, like for example, panel data analysis, where the time series element, cross-sectional elements also merge them together, pulled away, or maybe in some other manner. Then something called dyadic the structural equation model, multi-level structural equation modeling. And there is a mixture of distributions or the SEM, like the distribution measure may be considering the logistic regression, maybe covering some kind of exponential functional relationship. So these are the different advancement or the extensions of the structural equation model. And coming finally to the introductory part of the SEM, that what are the limitations? Limitations is that it reports the results in a very complex manner. It depends on the outset that it seems to be complex, but once we'll be detailed, going into the details of it, we can find that it is not so that complex in nature. If you can decode, or if you understand it in a very systematic manner, then the complexity can be handled. But anyway, it is not the simplest version of the analysis, like simple regression or multiple regression. Then the second part of the story is that we need a large sample for the estimation. Large sample is a debatable thing, but as a rule of thumb, if you are going for a cross-sectional data analysis, then the number of observations should be as large as possible. As large means if it is something called N, which is representing the sample size greater than or equal to 200, it seems to be a large sample size. And in other words, for 30, 40 observations, or maybe for a limited cross-sectional observations, this SEM is not a good idea. For the estimation purpose, we need at least 200 or 200 plus data size for the estimation purpose. Third point is that it is a complex analysis. Complex analysis because there's several variables depending on several other things, and then finally they brought into one table And then there is a possibility of different type of direct and indirect effect, mediation effect, and so on. So obviously, if there is a proper modeling, the fault arises, depending on where, the path, or depending on the determinants, etc., then the overall relationship interpretation or the inference will go wrong. So that's why, while addressing the complexity of the analysis, we have to be very careful, or we have to be very judicious in the manner the backup with respect to the theory or maybe the literature will play a very important role. So if you have a very proper backup and theoretical understanding, then this complex analysis will be running smoothly, and there will be less possibility of committing any fallacy. Otherwise, there is a high chance that because of its complex nature, we may end up with a very wrong analysis, and ultimately the relationship or the inference will be completely biased, inconsistent, and so on. Finally, the limitations of the model is that it is a misfit in the result, that it will be somehow that's what I am discussing in the third point, that if it is complex in nature, and if the proper what you call the precautions are not taken into consideration, then the corresponding estimations that we will be obtaining through SEM, they will be resulting to different biasness. So once it is biased, then there is a doubt with respect to consistency of the estimation, reliability of the estimation, and so on. So these are the limitations of the SEM. So with this background of the introductory part, then we'll be moving to the different jargons of the SEM model. Is it till now running smoothly? Am I a bit speedy, or should I little bit slow down,
Yes,
or
sir.
is
Perfect.
it
No,
okay?
sir, it is clear.
It's okay, sir.
Okay, thank you. So now moving to the different technical part, if you now disseminate, dissect what you call the SEM model is all about. So broadly, these are the four important, not four because they are actually associated with two components each. So accordingly, 8 to 10 points or 10 important things need to be understood. So let us start with the concept of called the observed variable and something called the latent variable. So suppose we are taking in the right hand side, there is a concept of aptitude. It may be research aptitude, it may be management aptitude, it may be anything else, right? So this aptitude is considered to be a latent variable because these are unobserved variables and we wish to have them observed. So these they can be thought of as underlying cause of the observed variables. They are represented by somehow something called oval. This is the representation style in SEM. So when something is represented in terms of a oval, or maybe somewhere in some other sockets also they are represented with respect to a circle. So whether it is a circular representation of a particular variable or maybe a oval representation, then we will be assuming that it is a what you call unobserved variable, which we call it as a latent variable. And this latent variable may depend on certain variable which is represented in terms of a square or maybe rectangle. Like over here, the SATV, SATQ, and HSGPA. These are certain variables which will be affecting the aptitude, and these are represented in a different manner. So these are called the observed variables. These variables that are included in our data set, that means we have some number, either in terms of what you call numeric variable, or can be something called categorical variable. It may be a continuous variable. So, but somehow these variables are observed, whereas this aptitude is not observable. On the basis of this observed variable, we can somehow generate this latent variable, and that is the subject matter of what we call the factor analysis that we are going to discuss shortly. So these variables like SATP, SATQA, HSPGA are observed variables in this path diagram. Anyway, this is not the starting point of the path diagram, but anyway, when we are linking 2 or 3 variables with respect to one variable, so that linkage needs to be described with respect to either is unidirectional arrow mark like this, or maybe sometimes the other way around. And accordingly, the other 3 terms which are represented over here, they are represented something called the error term. Anyway, this type of analysis we'll be discussing again further. Only one point needs to be clear over here is that there are certain variables which are unobserved, like aptitude, and there are certain variables for which we have some numbers. So quantifiable variables, observed variables, and they are represented like this. And observed variables, they are going to affect the latent variable. So that is the connection between the latent and the observed variable. Then moving to the concept of the path and covariance, what happens over here in the path? There are direct relations between variables. Estimated path coefficients are analogous of regression coefficients. They are represented by the straight arrow. So over here, we are discussing two variables. Previously, it was one. So now suppose we are taking two variables, and two variables are funding is one latent variable and aptitude is another latent variable. And aptitude depends on the three variables, and ultimately there are three error terms which are affecting the aptitude. Error terms over here means besides this SATB, there may be certain other variables which may be affecting aptitude that will be captured over here in terms of epsilon 4. Similarly, besides SATQ, there may be certain other variables they may be affecting aptitude, which is captured through epsilon 5 and so on. These epsilons are not only the what you call missing data, there may be with respect to some kind of functional framework problem, or there may be certain other things. These are the very important or very what you call popular terms in the econometric analysis, because error term is the backbone, or error term is what we call as the starting point of the econometric analysis. So these error terms are represented over here. Our focus will not be on the error term much, but anyway they will be discussed and they will be relevant also. But objective over here is that if there are two latent variables, then these two latent variables may be related with each other, and when they are related with each other, there may be a covariance between the funding and aptitude. Higher funding may leads to more aptitude, or less aptitude leads to more funding, whatever, either positive or negative correlationship exists. Then that particular relationship can be seen over here with respect to a array, which will be having two types, two direction wise. I mean, both of them are interrelated with each other. And that is the concept of covariance. We specify that the two latent variables or the error terms covary. Over here, the error terms are not mentioned as covarying, but there may be in some other type of modeling where the error terms also may also related with each other, like epsilon 1 and epsilon 2 may also related with each other. So in that way, a covariance type of what you call array may be fit over here in epsilon 1 to epsilon 2. It can be epsilon 2 to epsilon 3. It can be anywhere out. So that is the concept of path and the covariance. Paths are here like this: funding to grant, funding to scholarship, funding to stipend. These are the paths, and these are the something called covariance. Then the concept arises called exogenous and endogenous variable. So exogenous variable and endogenous variable, they somehow what you call remind us the concept of independent and dependent variable. The idea is more or less similar, but not the same. The difference between exogenous and independent variable, endogenous and dependent variable will be more clearer as we subsequently move further. But somehow, if this is the example where these are the something called observed variable, as we have seen previously, that if something is in rectangular or something called in square term, then they are observed variable, and these are the paths. So observed variable 1, 2, 3, they are affecting the first kind of variable called the scholarship, and somehow it should be represented in terms of oval shape, because it is the latent variable, or may not be a latent variable or observed variable. Here we are assuming it is an observed variable. So what happens over here? The determined exogenous variables which are determined outside the system of the equation, for example, these three variables, they are not depending on anything else. Or in other words, if you follow typically the path, diagram, there is not a single arrow which is beside or before these three variables. That means these are the variables, those who are starting point of the analysis, and that's why the arrows are starting from these variables to any one variable or maybe two variables. So that's why these are determined outside of the system of the equations. They are exogenously given to us. So there are no paths pointing to it. Rather, the paths are pointing from it to something else, some other variable. So these variables in this example are SATV, SATQ, HSGBA, and something called creditors. Why this fourth variable over here? Because this fourth variable is also affecting the final variable over here, but no arrow is actually following before it. So that's why 1, 2, 3, and 4, these four variables are called exogenous variable. And any variable which is actually at least getting one arrow towards it, and like scholarship over here, it is getting 3 arrows towards it. FYGPA, it is at least covering 2 arrows towards it. It may be 1 arrow also towards it. Then in that case, we cannot consider it as a exogenous variable. Rather, they are determined within the system. That's why we called it as an endogenous variable. So endogenous variable are determined by the system of equations. At least one path points towards it. And the variables scholarships and FYGPA, scholarships over here, because these are the 3 things which are moving towards it. In addition to that, there is error term also, and FYGPA, because scholarship and creditors, they are affecting it in addition to another error term. So in that way, because multiple arrows are towards it, that's why these 2 variables are endogenous and not a single arrow is before them. So that's why these are the 4 variables which are exogenous. Then there are certain other versions of the endogenous and exogenous variables also, like the previous analysis called observed and latent. Latent means those who are unobserved, and observed means those who are actually measured measurement thing, which for them we have some data with us. Some what you call quantifiable mechanism is available, and on that basis we have some data, we have some numbers for them. So in that way, if they are exogenous, then accordingly observed exogenous or observed endogenous. And if the variable is latent, then on that basis also it can be latent exogenous and latent endogenous. So observed exogenous is a variable in a data set that is treated as exogenous in the model. That means in the similar manner over here, there will be something like over here, these variables are observed exogenous because as you can see, they are not in ovals. Rather, they are in something called in the square or the rectangular manner. So these are the 4 things which are what you call observed exogenous in this case. But latent exogenous is not mentioned over here. So anyway, there is no latent variable over here. As you can see that there is no what you call the variables are not in oval set. They are not represented over here. So in that manner, the latent exogenous, observed endogenous means it will be determined within the system. Like over here, scholarship and FYGPA, they are one endogenous variable, and because they are represented in terms of square or the circle, square or the rectangle, so accordingly we cannot consider them a latent endogenous. Rather, they are something called observed endogenous. So all the variables in this model, they are observed variables. And depending on the nature of the arrow path, so these 2 are observed and endogenous, and these 4 variables are called observed exogenous. Taking some other suitable models subsequently, we can discuss all these 4 types of models in a detailed manner further, right? So if you have any doubt or confusion, then just wait for 5 to 7 minutes. All those variables, all those discussions will be more clearer by taking some suitable examples. Then the last technical jargon is something called recursive or the non-recursive system. So basic thing behind recursive and non-recursive system is that, like over here, 3 variables are affecting the weight, price, foreign, displacement, any 3 variables like this. And length and weight is going to affect something called MBZ. So over here, what happens, if you follow the arrow path, these arrow paths are always in directions to one way. Rather, these 2 variables are not interrelated with each other. That means weight is not going to affect length, or length is not going to affect weight. So if there is a 2 type of directions like over here, then we call it as this type of representation as a recursive model. Recursive models do not have, this is something called recursive model, where the models do not have any feedback loops or correlated errors. That means if you have something like this type of measurement, then there will be a possibility of recursive model method, recursive method, because these models do not have any feedback loops. That means weight and length or price, foreign, displacement, they are not having 2-way relationship like over here. the strain and the satisfaction, they are having two-way relationship. Strain may affecting satisfaction. Satisfaction may also affect the strain. Positive, negative, that's a different story, but they are somehow feedback relationship arises. Or there is a correlated errors also. Like over here, the error term 1 and 2, they are also correlated. So in both the cases, both the models are not recursive. Non-recursive because here the error terms are correlated with each other. Here the two variables are correlated with each other. If there is no such things happen, like the previous analysis over here, like this model or maybe this model, these are something called the recursive model because these are not interrelated with each other. Anyway, these particular variable which is correlating the covariance between each other, that is not a problematic situation over here. These covariance may exist between the two variable, but somehow the two prominent variable like here, either they are interrelated or they may be interrelated over here. So these error terms may be interrelated with each other or they may not be interrelated with each other, but they will be capturing the covariance part. So that is the difference between recursive and non-recursive. The major important variables should not have two-way relationship. If they are exist a two-way relationship, then they are non-recursive. And if there is a two-way relationship exists, non-recursive models have feedback. So these are feedback relationship. It's a non-recursive model. And where there will be no feedback relationship, then we call it as a recursive. Recursive is a relatively simplest version, but in the model building portions, we may somehow come into the non-recursive part also, where there is existence of feedback relationship. So till now, these are the technical jargons part is over. If there is any doubt or any question related to this, you are most welcome, so that we can move to the next part of the discussion called the types of SEM. Is it okay till now? Any doubt with respect to the jargons or maybe the previous discussion?
Yes, sir.
Okay. If no, then the next topic is the types of SEM. The types of SEM is broadly can be divided into two categories. That means there may be a structural equation model where there is only one endogenous variable, or there can be a structural equation model where there are two or more than two endogenous variables. So if there is a one endogenous variable, then it may be that endogenous variable may be something called observed endogenous variable. So if there is an observed endogenous variable, then again subsequently it gives rise to one exogenous variable or more than exogenous variable. And this will be giving rise to simple regression, multiple regression. Similarly, two or more endogenous variable can be observed variable or latent variable. And these observed variable are somehow related to, like this gives rise to multivariate or path analysis. And latent variable gives rise to this. So these are in nutshell the total types of SEM, but to get to know more about it in a very detailed fashion, we have to divide them into different parts. So let us do that. And before going to do that part, okay, I will come to this particular part at the end. Let me move to the first part of the story. So one endogenous variable, and that one endogenous variable, if it is an observed variable, then there are two possibilities that that observed variable may be exogenous variable or there may be more than one exogenous variable. If there will be one exogenous variable, it's a simple regression. If there are more than one exogenous variable, then it is a multiple regression. What does it mean? See the lower portion of the analysis. In a simple regression, what happens? There may be a variable called x1 and there may be another variable called y1. Both of them are represented in terms of a square or the rectangular fashion. So no need to say that the variables are in the observed category. They are not latent category. Now what happens over there? There is a relationship over here that one variable is exogenous. That means this x1, because it does not have anything path before it, any arrow before it. So we consider it as a x1 as an exogenous variable. And if these exogenous variables are more than one, like over here, then accordingly x1 and x2, two variables are affecting y1, then accordingly it's a multiple regression. It's a simple case. We should not spend much time over here. Only thing is that there is a one dependent variable and there is a one independent variable concept. And that dependent variable is also known as endogenous variable in this model, and this endogenous variable is observed. It's not a latent variable. And similarly, the independent variable, is considered to be an exogenous variable over here, and this exogenous variable is also not a latent variable. Both of them are observed variable, and there is a one direction. Only one factor is going to affect y1. So that's why we consider it as a simple regression model. Whereas if the y1 is getting affected by multiple variables like x1, x2, x3, x4, etc., then accordingly it can be modeled further complex manner. But for the simple case, if you assume that if there are only two variables which are affecting y1, then this is the representations of a multiple regression. And obviously, each of these variables, they have their own error terms. There may be correlation, covariance between these error terms, or these two variables may be correlated with each other and so on. So in that way, there is a concept of multiple regression. Majority of the time, these type of reputations are not perfect. For that, I have some more detailed explanations for that. So this is a representation of a multiple regression. So x1, y1 is beta 1, 0, which is a constant term. Beta 1, 1, x1, beta 1, 2, x2, beta 1, 3, x3, and it can be extended to further n number of variables. And there is a epsilon 1, which is the error term. So error term is going to affect y1, and x1, x2, x3, they are also getting affecting the y1 in terms of beta 1. So beta 1, 1 is representing the coefficient. That means if there is a change in x1 by 1 unit or 1%, depending on the functional representations of the model. If it is linear like this, there is no log component over here. Then what we can say that if there is a x1 unit increase, if there is a 1 unit increase in the x1, then there is a beta 1, 1 increase or decrease depending on the beta 1, 1 sign, whether positive or negative, and that is going to affect y1. So in that manner, this is the representations of something called a multiple regression, where example is like y1 is high blood pressure. This high blood pressure is maybe functioning of overweight, maybe smoking habit, maybe because of the stress factor. Each of them individually, they are affecting the high blood pressure component. And if you have some other variable, some other measurement error, that can be captured through this error term. So that is the concept of the previous analysis called there is a one endogenous variable, observed variable, more than one exogenous variable, and gives rise to multiple regression. So this is first part of the story in terms of the SEM typology. Second part of the story, all these parts are actually coming from this model. So we are discussing these part portion in a separate manner, these blue portions. Now we are going to the portions called the SEM, where the two or more endogenous variables and one will be observed variable, and we are going to discuss this second part of the story. So second part of the story says that if there is a two or more endogenous variable and both of them observed variable, then there is a possibility that the observed variable may be exogenous to endogenous, or it can be endogenous to endogenous. So if it is exogenous to endogenous, then there is a multivariate regression. And if it is endogenous to endogenous, there is a path analysis. What does it mean? Besides going to this type of discussions, let me go into the case called multivariate regression. So what happens over here? We need at least two variables over here. Two variables will be y1 and y2. They may be latent variable, they may be observed variable, depending on the nature of the question, nature of the research question. Currently, we are taking two latent variable over here. So these two latent variables are y1, y2, endogenous variable as well as dependent variable, you may say. Now, what happens? This y1 that is getting affected by the four variable called x0, x1, x2, x3. Whereas this y2 is also getting affected by the same set of variables. It may be same set, there may be different set also. That will be the second part of the story if you want to make the analysis a little bit more complex. What happens over here? The simple fundamental concept is that two dependent variable may be getting affected by a set of independent variable. They may be same, there may be some difference. Like for example, first three variable, they may getting affecting x, y1, fourth one is not going to affect. Or the last three variables, they are going to affect the second dependent variable, but not the first one. That may be possible. So it is not only the case that whatever may be the independent variable, they are going to affect uniformly to both the variables. That may be the case, may not be the case. So in this type of case, we call it as a multivariate regression. The difference between multiple and multivariate is that in multiple, we are getting only one dependent variable. There are no y2, y3 over here. But over here in a multivariate analysis, there are two or more than two what you call dependent variable or what you call endogenous variable. So that is the fundamental concept of the multivariate regression and multiple regression. So in this case, what happens? How do you distinguish between multivariate and path? Here, the no covariance among independent variables is x1, x2, x3, or x0. These variables are not related with each other. We are not going for its correlationship analysis. They may be correlated with each other, but in multivariate regression, we are assuming them that they are not correlated. So obviously that is not a good idea, but that is the philosophy, or that is the assumption behind a multivariate regression analysis. And the second analysis is that no causal relationship between dependent variable y1 and y2. And these two dependent variables also, they need not to be having any relationship. Either y1 is not going to affect y2, or y2 should not going to affect y1. That type of relationship analysis is ruled out in multivariate regression. Whereas in case of path model, these are the two limitations which is captured over here in case of multivariate regression. They're actually considered over here in case of the what you call the path analysis or the path model. So what happens over here? If you consider three variables called x1, x2, x3, all the three variables are going to affect y1 and y3, y2. And now what happens? The previous assumption that x1, x2, x2, x3, and x1 to x3, because there are three exogenous variable or independent variable. So there is a possibility of three type of relationship. First independent may be related to second. Second may be related to third, and first may be related to third. So if this is the nature of relationship, then that is captured under path, not under multivariate analysis. This model here, these things are not captured. So that is the difference between a multivariate regression to a path model. Whereas the second assumption which is ruled out over here, there is no causal relationship. So that causal relationship is also captured over here, where the y1 is going to affect y2. The relationship may be the reverse way also. The y2 may also affect y1. Or there may be a feedback relationship also, that y1 and y2 both are affecting with each other. So in that type of analysis, we are going for a path analysis or a path model. So this is the second part of the story, going to the first thing. So this is the first part, simple multiple, then it is a multivariate and path analysis. Then subsequently, the last part of the story of the SEM model is that, the last part of the story is that if the two or more endogenous variable, and these two more endogenous variables are latent variable, then they are give rise to something called factor analysis or structural analysis. Latent variable, if it is latent to observed, and latent variable is something called latent to latent, then that is the difference between this factor analysis and structural analysis, structural regression. So how they are affecting with each other. So as you can see over here, that there is a endogenous variable or the latent variable over here. This is not endogenous, rather latent variable, because it is in oval and there is no arrow behind it. So that's why it is not endogenous. So it is a exogenous variable as well as a latent variable. So this latent variable, they are going to affect y1, y2, y3, those who are observed variable. And this is the nature of their factor loading or something like that, which we call linear factor analysis. And then in that type of analysis, we call it as a factor analysis, because there is a latent variable which is factored by these y1, y2, y3. Whereas over here, what happens? X1, x2, x3, these variables are affecting one set of latent variable. X4, x5, x6, they are affecting another set of latent variable. And these two latent variable is going to affect another latent variable called eta1, which is also a function of y1, y2, y3. These y1, y2, y3, these are certain variable which is going to ultimately affect some eta1, and this eta1 is going to be affected by two latent variable, and these two latent variable have their own way. So that is the difference between something called factor analysis and structural regression. What happens over here? We are going to discuss only one part of the story over here. Like if you disseminate them, this part of the story is one factor analysis. This part of the story is another factor analysis. This part of the story is another factor analysis. So there are three factor analysis which is already there in the structural regression. So once they are generated like this manner. So this is part one of the story. This is part two of the story. This is part three of the story. So these are factor analysis individually. Then factor analysis plus the path analysis. That means when We are clubbing this epsilon 1 and sorry, xi1 to this eta 1 and xi2 to this eta 2. So then we are going to give a structure to this particular path. I mean, the structural path to this particular variable. These two latent variables, they are not interrelated with each other. Rather, the path says that they are going to affect only eta 1 in a uniform manner. There is no feedback over here. There is a single relationship, and this is moving from xi1 to eta 1 and xi2 to eta 2. So these two line is actually nothing but the path. So when this path is actually clubbed together with this factor component, then the overall analysis is called the structural equation. Moving further to give a better discussion. So there are three latent variables over here: xi1, xi2, xi3. Xi1 is a function of x1, x2, and the xi2 is a function of x3, x4. Xi3 is a function of x5, x6. So what happens over here? This xi1, how they are generated. Xi2 is how they are generated from x3, x4. Xi3 is how they are generated from x5, x6. That is the concept of a confirmatory factor analysis, where these latent variables, they may be covariant with each other, correlated with each other. First latent variable with second, second with the third, and first with the third. There may be, there may not be. These are not hard and fast rule. But these type of analysis is called confirmatory factor analysis or simple factor analysis. That we call it as a measurement model. Whereas when you club them together, now what happens over here? This xi1 is independently. This part of the story is one factor analysis. This part of the story is second part of the factor analysis. This is third part of the factor analysis. This is fourth part of the factor analysis. There are four endogenous variables. These are four endogenous as well as latent endogenous variable. These are the different indicators which are affecting one part of the confirmatory. These are the second part of the confirmatory. These are the third part of the confirmatory or another type of variable eta 1 and eta 2. And finally, when they are clubbed them together, xi1 and xi2 going to affect eta 1 and eta 1 is going to affect eta 2. When we are clubbing the factor analysis along with this arrow mark, this is nothing but the path portion or the path diagram portion or the path analysis part. So that's why the path analysis plus this individually factor analysis, this brought them together, combined them together, gives rise to the structural equation model. So these are in nutshell the several portions of the what you call the structural equation modeling. So now if you move back to the discussion that we left here, so what happens over here? So there is a exogenous latent variable, and this exogenous latent variable depending on three observed variable, and these three observed variables that are going to affect the exogenous latent variable, and these are the different factor loadings that we call it as a, in terms of factor analysis, we are considering them as the factor estimates. And now the y side of the measurement is that there may be another latent variable which is affected by another three variables over here. Now what happens? This latent variable and this latent variable, they are related or they are connected with each other with respect to this path analysis or path model. This is the only path model over here in a simplistic analysis. So one latent is a function of three determinant, second latent is a function of three determinant, and when the first latent is related to the second latent somehow by the connection over here, this is nothing but the what you call the path analysis, and combine them together, this is nothing but factor 1, factor 2 with path is nothing but the structural modeling. Is it clear till now? Because this is already a the soul of the SEM is discussed till now. So if there is any doubt or confusion, please tell me. Otherwise, once we go to the details of the STATA analysis, then it will be further confused. Is it okay?
Yes, sir.
Okay, fine. So now let us go into the technical part, that now if you are going to build the SEM, then what may be the steps associated with generating them. So one is, first thing is that there is a necessity of a hypothetical relationship between different variables. So we need to find out, or we have to specify our model. So first step is specification of model. Second thing is that whether that model which is specified whether there is a concept of identified model, or it is a over-identified model, or it is an under-identified model. Just identified model indicates that if the number of unknowns equals the number of free parameters, the number of unknowns means, suppose in the previous model over here, in this case, the number of unknowns is this. This is one unknown, this is second, third, and fourth. So in this model, there are four unknown thing, because they are generated within the system. So there are only four unknowns. And if these four unknowns are equal to the number of free parameters indicates that these are all free parameters: x1, x2, x3, x4, x4, x5, 6, x6, and these are all. So what we can see that 3 plus 3, 6 plus 3, 9 plus 3, 12. So these are the 12 what you call the variables over here. So these are the 12 variables, and or in other words, these are the 12 what you call the factor loadings. So if the factor loadings are exactly equal to this type of observable, that means the endogenous variables are 4 and the factor loading individually are also 4. If in a model found to be 4, then we call it as a just identified model. So majority of the cases, the models are over-identified. Over-identified means the more knowns than the free parameters. So for free, I mean more knowns means these are all the known variables, and these are unknown variables. So obviously the known variables must be very large in comparison to the unknown variables. If that is the case, then we call it as over-identified. And under-identified is that the number of unknowns is greater than the number of parameter. Model coefficients cannot be estimated, because it is simple the case. Just imagine a there are two equations. The first equation is y is a function of x1, x2. Second equation is also another variable called y2, which is a function of also x3, x4. Now what happens over here? There are in the first equation there are three unknown variables: y, x1, x2, y1, x1, x2. In the second equation, there are three unknown variables: y2, x1, x2. Only thing is that here the number of knowns and unknowns variables are 3. Number of unknown variables are 3 plus 3, 6, but the equation is only 2. So in that case, we cannot solve the problem, right? In a simultaneous equation model, if the number of unknowns is equal to the number of equations, then only you can solve the problem. If that is the case, that is nothing but a just identified problem. If the number of unknowns is actually more and the number of equations are less, then we call it as under-identified. Normally, in a just forget about structural equation modeling. I'm just talking about a simultaneous equation, what you call equation. When there are two equations and two unknowns, then they can be easily find out. Then it is a just identified. If there are three equations and two unknowns, then also it can be found out, but there is a possibility that each variable may have two or more than two variables. Then we call it as over-identified. Over-identified is okay, but under-identified indicates that if we have something called three unknowns and we have only two equations. So in that case, that cannot be solved out at all. So that is the concept of under-identified. So these are the three things which is coming under the SEM model also, in depending on this framework called over here. So we have to be very careful that whatever the endogenous variable needs to be generated, they must be relatively less in comparison to the variables over here. They must be relatively high, which is a normal assumption, and this is not a very challenging thing. Now coming to the parameter estimation, it has two parts. Like in any hypothesis testing, we have something called observed model and something called the fitted model. So there is a comparison take place between actual and estimated coefficients or something like that. Then on that basis, we can get to know that whether the hypothesis is verified or not verified, statistical significance, and so on. So these are all also affecting, these are also the case in case of the SEM estimation. And then subsequently, once any estimations took place, we need to understand that how robust that model is. So for the robustness checks, there are certain checkpoints. And then once the checkpoints are giving green signal, then the model is accepted, no further change is required. But if the checkpoints or the diagnostics checks or diagnostic things they are somehow orange or not so green kind of thing, then there is a possibility or there is a signal for some kind of modification required in the existing model. So that's why we do a model modification. So in that way, any econometric analysis or any statistical analysis that we do, the same principle follows in majority of the cases, whether it is multiple regression or multivariate or any factor analysis or something like that in SEM. So moving further, the first point is the development of hypothesis. So SEM is a confirmatory technique. So like this over here, what we are seeing over here. So that is the concept over here. One, we have to generate that we have to generate a variable in such a manner which is going to affect two other variable, and these two other variables may be interrelated with each other. If you relax this assumption, the hypothesis is different. The first variable is going to affect second, the first is going to affect the third, but first, second, and third, they are not related. So if that is the hypothesis, then accordingly, this will be a different hypothesis in comparison to the same this hypothesis only. Or it may happen the first model is going to affect the second. The first is not going. The first is going to second. The first is not going to affect the third directly. Rather, first is going to affect second, and second is going to affect third. If that is what you call the hypothesis you develop, then accordingly the finding will be different. So first thing is that how do you formulate the hypothesis, and no need to say that in majority of my lectures in many organizations or many platforms, I repeatedly say that all these hypotheses and all these things depending on our theoretical understanding or the literature survey properly. If you get to know the logic behind the relationship between two or three variables, then only that will be easier or that will be logical enough to approach the model. Otherwise, as I practice poor jokes many times, that if there are two variables, like monkey is jumping from one branch of the tree to another in a forest, and if you find out it's something how frequently it is jumping or whatever, some x variable, then this is one variable. Second variable is a fish in the pond, right? So how frequently it is moving from one part of the pool to another, or maybe smoothly running or under the water or whatever, and find out it's some kind of survey we do and report the frequency or something like that. Then one variable is x, another is variable is y. The first variable is the monkeys jumping in a forest. The second variable is fish movement in a pond or something like that. And then we'll bring them together and say that, see, this is x variable, this is y variable, and y is causing x or x is causing y. That means monkeys jumping in forest is causing the fish movement in a pool, which doesn't matter, which is a a rubbish hypothesis, isn't it? So it is not based on any logic. And do not forget to understand this thing also, that theory does not necessarily mean that always a literature is available, always somebody said something about a particular thing, and then we are going to test that component. It may not be the case. Theory is nothing but a logical approach. For logical approach or relationship between two variables, we have to assume something. And that assumption, if it is more realistic, then that hypothesis will be more realistic, and it will give rise to some fruitful inference. Otherwise, there is no inference. And if you just fit a regression between the monkey and fish example right now, there may be a statistical significant relationship also found, but it does not mean anything. So that's why this is the first point, and this is the most important thing, that how do you develop your hypothesis? It must be backed by a logical approach. And if that logic comes from a theory or earlier previous literature, then fine. Otherwise, you have to develop something which will be logic based, assumption, realistic based, and so on. I think I am making sense till now. Is it? Hello?
Yes, sir.
Are you feeling bored or something like that? I mean, the voice is going to be, weaker and thinner gradually. I'll be poking all of you in between because as I told you that this is not a physical mode, so I cannot meet you personally. That is the limitation as well as advantage of a online meeting like this. But
No, no, no,
somehow
sir.
if I come,
Interesting. Topic is very interesting.
okay, fine, thank you. So now moving to the construction of the path diagram. So first thing is that the model or the hypothesis needs some variables, which variable endogenous, exogenous, observed, latent, whatever, they needs to be defined properly. Then the second model is that something called we have to construct the path diagram. So as you can see over here, that this is the nature of this construction of path diagram. So what we have to find out that once we design that this there are three what you called endogenous sorry there are three latent variable. This latent variable is exogenous latent variable. These two latent variables are endogenous latent variable, and these are developed under the first step when you develop the hypothesis. Then in the second part of the construction of path diagram, the first latent variable is going to affect, and the second variable is going to affect. First also is going to affect the third one. So this is the path of this model, and this particular variable called two, it has three or more determinant. The third Latin variable, it has also three or more Latin variable. And the first Latin variable is also having multiple determinant, like over here, three Latin variable. So this is the way in which we can define, as I have promised earlier, that when we discuss the Latin variable concept, the endogenous and exogenous. And why we'll call it as exogenous? Because no arrow is moving towards it before that. Whereas this latent variable, at least one arrow is towards it. This latent variable is at least one arrow is towards it. So if there is a possibility of that, there is another arrow towards it also. So in that case, this may have multiple arrows towards it, but at least one is giving rise to endogenous variable, and no arrow before it is defining something called exogenous latent variable. So this is the way in which the path diagram is constructed. Now what happens over here? Moving further to the path analysis, then we are going to something called the measurement model. So measurement model indicates that the different confirmatory factor analysis over here. So these are Xi1, Xi2, Xi3. These are something called eta1, eta2. Eta1 has several determinant, eta2 has several determinant. When we are analyzing them in watertight compartment, these are measurement model, which is nothing but confirmatory factor analysis or simple factor analysis. Forget about confirmatory factor analysis. These are the two versions called confirmatory and explorative. So that we will be discussing when we are going to the STATA analysis with the example. Till now, this is the part of the measurement model or the factor analysis. Now, what happens over here? Once the measurement model is defined, then we'll be going for something called the path diagram. So path diagram indicates that the Xi1, Xi2, they are interrelated, Xi2, Xi3, they are interrelated, Xi1, Xi3, they are interrelated. And now Xi1 is going to affect and Xi2 is going to affect eta1. So Xi1 and Xi2 is going to affect eta1. Xi2 and Xi3, they are going to affect eta2. So these are nothing but a multivariate regression type of thing. And these are nothing but path analysis because these are overlooked over here. And eta1 and eta2, they are actually interrelated. Eta1 is going to affect eta2. So at the end of the story, our focal point of analysis is eta2. Eta2 is a latent variable which is not observed. This is directly related to eta1. Eta1 is another latent variable which is not observed, and this eta1 is depending on two variables. Now this eta2 is also going to be affected by Xi2 and Xi3. Xi2 has two variables as a determinant. Xi3 has two variables as determinant. And this eta2 is not only affecting by Xi2 and Xi3, it is also getting affected by Xi1. How? Because Xi1 is going to affect eta1 via lambda1, sorry, the gamma 11, and through this gamma 11, it is also going to affect eta2. So in that way, all the variables called Xi1, Xi2, Xi3, and eta1, they have some types of effect or impact on eta2. So when our objective is that, how do you find out that eta2 is, depending on? So eta2 is not only depending on by only y3, y4, Rather, they are also affected by all those parameters, because once we say that 1, 2, 3, and 4, they are going to affect eta 2. This 1 is a function of 2. This 2 is a function of another 2. So if you say that all those 6 plus all those 4, these 10 variables, they are also going to affect eta 2. So that is the beauty of structural equation model. How do you make a large variable going to affect one important variable, and what are the different layers of it? So x1, x2, they are going to affect xi1. Xi1 is going to affect eta1. Eta1 is going to affect eta2. X3 and x4, they are going to affect xi2. Xi2 is going to affect eta1 as well as eta2 directly. And xi2's effect on eta2 via eta1, that is also captured. So that is the beauty as well as the complexity of the structural equation modeling that we are going to discuss in by taking some suitable example. By now, the soul or the philosophy behind of structural modeling is clear, I guess. So these are exogenous and endogenous latent variable and so on. So once we do the model, then these are the different goodness of fit modeling test. So assessing the model goodness of it, these are different other technical part of it. These are not so we worried, because as we know that once we do the ANOVA analysis or any kind of multiple regression testing analysis, we are interested to focus on certain key parameters and what are the permissible guideline for them. So that is the objective over here. So these are the different assessing of modeling goodness of it. If you can understand its the technical part is fine. Otherwise, I am going to skip them as quickly as possible, so that we can spend some more time in doing the hands-on training session. So these are all likelihood ratio chi-square test. This is one indicator, and this is based on something called saturated model, baseline model, and specified model. These are likelihood ratios. As I have told you, I am skipping them. If you have any further discussion on each of them, you can stop me and tell me what is that, why so, what would be the interpretation, and so on. I am ready to do that, but for right now, I am going to skip them, just to telling you, informing you that these are the certain things which needs to be understood before going to test whether the model is good or bad. So first thing is that a chi-square test, which is a comparison between a baseline and a saturated model. And these are the technical portions. And ultimately, what we are interested in that, if there is a chi-square test available, find out its p-value, whether this chi-square test is statistically significant or not. As we know that p-values concept says that, I'm sorry, this p-value goodness of it is indicated by p-value is less than 0.05. I'm sorry for the typo error. So it should be less than or equal to 0.05. So if it is the case, then accordingly, the chi-square test is satisfied. And on that basis, we can say that this is the model which is good or bad. So this is first part of the story, likelihood ratio chi-square test. Second part of the story is actually two parts. One is Akaike and square spatial criterion. So these two criteria says that these are not meant for a single run modeling. Rather, if you have a multiple run modeling, that means suppose you test for one type of model, and then you do some logarithmic transformation, or some path is not covered in the first model specification. Then in the second model specification, you build some other type of path. Then that will give rise to another model. So when we have multiple models, by doing some changes in the initial model to new model, then AIC and VIC, AIC stands for Akaike Information Criterion and Square Spatial Information Criterion. These are the two criterion which will give us a comparative fitting of the model. So comparative fitting of the model is that lower is these two variable good for the model. So if the model 1, AIC and VIC must have some scores, in model 2, the AIC, VIC must have some other scores. If the first model AIC is less than the the second model AIC, so in other words, because AIC is less in first model, model 1 should be preferred over model 2. And same is also the case for VIC. It cannot be the case that if AIC is less in model 1 in comparison to model 2, BIC will always will be greater than model 1 by model 2. That cannot be the case. It should be in the same direction wise. Hardly there is a chance that that type of possibility may arise, but majority of the cases the uniformity holds over here. So it will only give you an idea that if there are two or more models available, then how do you compare that whether model 1 is good or model 2 is good. So model 2 is the modified model, and model 1 is the initial hypothesis that you have taken into consideration. So that is the idea behind this AIC and BIC. Then, as you know, again, there is a problem over here. It should be determinant of xi hat and determinant of sigma hat over here. This is a normal coefficient of determination of R square model. So that means if higher is the R square, more is R square actually a value which will be a goodness of fit measure if it is known to you earlier. Broadly, it varies between 0 to 1. Closer to 1 is good, more, I mean, better fitness. And if it is closer to 0, then it is relatively less fit. And the objective is that if you have getting some R square closer to 1, then that will be good for the model. So this is next thing. In what is called structural equation modeling, there is another part called root mean square error approximation. So this root mean square of error of approximation, it compares the current model with the saturated model. That means when we are going for a model specification by doing some path analysis and factor analysis, then it will give you a saturated model that is the best outcome possible. And there is a current model. The current model will give you some portions of the saturated model. If that some portions of the saturated model will be covering more, then accordingly it will be a good model. So that's why this root mean square error is actually relating to the chi-square distribution, and this chi-square distributions minus the degrees of freedom. This has a what you call formula. And ultimately, what we are interested in by clicking of a mouse, you will get all the results. That is not a big problem. But now the situation is that if you are getting a value of RMCA which is very high, then this is not a good model. Rather, this root mean square error of approximation should be as minimal as possible, or at least it should be less than 0.06. Again, there is no rule written anywhere that it should be the always case. It may vary between something called 0.05 to 0.08. But the rough idea is that if something is more than 0.1, definitely that model is not good. If it is lying between 0.05 to 0.08, then it is adequately fit. And if it is definitely less than 0.05, then it is relatively the best model. The usual version that we are going for what you call p-value analysis. That means if the p-value lies between 0.00001 or very lower number to 0.01, then it will be the 3-star P, then it will be 2-star P, then it will be single-star P. There is no such star component over here, but this is the idea behind the RMSEA, which should be as minimal as possible. Then it is good for the model fitting. Now, again, there is a error over here. It is 1 minus numerator is this divided by the denominator is like this. It is a CA5, which is a comparative fit index. It compares the current model with the baseline model. So there is a saturated model, there is a baseline model that we have, I think we skipped that model previously. So this saturated model, it assumes that all the variables are correlated. The baseline model, it assumes that no variables are correlated except for the observed exogenous variable when endogenous variables are present. And there is a specified model, which is the model that we fit. So this specified model is in our hand. This baseline and the saturated model that the system will generate with each other. From the system, it will be generated. So our objective is that the specified model and the saturated model relationship and the specified model and the baseline model specification should be holding. If that is not the case, then our model is not good fit. So that is the idea behind here. So if you find out, it compares the current model with the baseline model. And this current model, if it is covering a majority part of the baseline model, and that's why if it is a very high score, sometimes 0.9, sometimes greater than 0.95, it cannot be more than 1 because this is the definition of it. So if the numerator is 0, then only CA5 will be what you call 1. But there is no such possibility of getting it more than 1 or less than 0, because if these two numerator and denominator are equal to each other, then it will be 1. So 1 minus 1 is 0. And if the numerator is only 0, then it will be 1 minus 0 by something, it will be 1. So it will lie between 0 to 1. And if it is closer to 1, then only it will be the case. So 0.95 means it will be 1 minus, this will be 0.05. If it is 0.5, then accordingly, this particular ratio should be very less. If the ratio is very less, that means the numerator should be very less in comparison to the denominator. And on that basis, we can say that the CFI is an indicator of the goodness of it. Higher is CFI, good for the model. And another version is like TLI, which is called Docker layers model. The similar type of approach is here. The similar type of inference, if it is greater than 0.95, then also it is good. TLI and CFI, they go hand in hand. And there is finally a model called standardized root mean square residual. So a root mean square residual is a measure of average difference between the observed model and the implied correlation. This will be close to 0 when the model fits well. So lower is SMR, SRML, that will be good for the model. Higher is not good. And if it is a suggesting value called 0.08 or below, then it is good for the model. So kindly keep these components ready. I mean, in a different, just write down them previously. So I am just revising again, once again. So chi-square model should be statistically significant, number 1. AIC, BIC, if you are comparing, lower AIC is good and higher AIC is bad. R square close to 1 is good. Root mean square is something called greater than 0.1 is the best, worst, and less than 0.05 is the best. CFI greater than or equal to 0.95 is best. TLI greater than or equal to 0.95 is best. SRMR less than or equal to 0.08 is good. Lower, further lower is very good. So that is the idea. So in a nutshell, I have brought it from some other sources. So these are the idea behind it. Anyway, the slides will be available to all of you, so you can read it on your own. Whatever I have discussed in the last 7 to 8 slides by taking the different goodness of it indicators. These are summarized over here in this particular table. And this table is borrowed from some other sources. This is not mine. Next fundamental thing is that by doing all those diagnostic checks, if you find that there is a necessity of a model remodification or modification is required, then accordingly we'll do the modifications. So now coming to the different popular SEM software packages, these are the list of these. No wonder that this is the model which will be associated with the SPSS, the statistical package for social sciences. And majority of the SEM, I mean, like when you are doing a social science software analysis, then SPSS considered to be the best one. And similarly, when you are going for SEM analysis, a sister version of SPSS is something called AMOS, which will be considered to be the most popular software packages. Though there are multiple others are available, I am going to referring to STATA. The regions are very simple and straightforward because I have little bit more comfortability. It is related to the comfortability because of my comfortable zone is STATA handling. So I am going to do that. But frankly speaking, if you are a SEM user going for SEM modeling, then AMOS will be the best one. I do not, I mean, reject that recommendation that higher versions of sophisticated softwares like R, Python, I do not know about MATLAB, whether it can handle or not. I'm sure it can handle. Then all those models are good. Just a usual disclaimer applied over here that software packages are only like video games, right? So if you are accustomed with a particular video game, how to handle a video game, then it may differ from one video game package to another video game package in terms of something called the visual, maybe sound effect or something like that. So there is no such very fundamental difference between them. But that does not necessarily mean that if you do a simple regression analysis using STATA by views or maybe SPSS, the same exact result will come. It may have a very differential result may come, very differential, but more or less if something is found to be significant, it cannot be the case that it found to be insignificant in some other software. So broadly, what my point is that that use any software where you find yourself comfortable. Same logic is applicable to me also, and following that logic, I'm going to use the next 50% of the discussion with respect to STATA. Is it fine? Is it okay?
Yes, sir.
Okay. Just give me a minute. Let me have a water, please. Just give me a minute. Okay. So now moving further, so I had almost 75 or 76 slides. So fortunately or unfortunately, I have covered up to 45 slides. So I am running well as per my expectations or my analysis. So before going to do the next analysis, I just want to highlight you. There is an Excel file again that I'll also be sharing with you, all of you. In this Excel file, I have certain data files with me. So there is a SEM1, SEM2, SEM3, SEM4, and SEM4 has certain more informations with respect to raw data. So what we are going to do in the subsequent thing, I could not find, frankly speaking, a particular well-tested Excel file where I can execute each and every one of them in a very lucid manner. That means by running all those models and then simultaneously telling you the story, interpretations, etc. I'm sorry to say that I could not find. That's why what my objective is that in the PPT, I have some informations about the STATA results and so on. Initially, some portions that will be related to this SEM1 analysis, I'm going to do it with the help of STATA, and then I will come back to the slides over here, and then we can compare whether we are getting the same result, different results, etc. Obviously, we'll get the same result. Then how to interpret it. And the story will continue up to the completion of the factor analysis part, that means data analysis part 1. If you remember, in the outline, there are 3 data analyses. So first part of the analysis, I will be doing it and demonstrating it with respect to PPT and its interpretation. But somehow the entire version I could not get it from some sources. So that's why the example files will be going to change from factor analysis to path analysis, from path analysis to another structural equation analysis. But more or less the line of argument of doing this exercise will remain same, remain constant. Only thing is that they will be treated in separate piecemeal approach, number 1. Second thing is that the first piecemeal approach can be done both manually as well as with the help of PPT. But the second and third, that means the path and as well as structural analysis model, I will only tell you the final result by doing the command, etc., and then its interpretation. And there is a SEM4 model over here that you can see. I will use this model to finally demonstrate it in terms of a graphical manner, where both the STATA command as well as the result can be demonstrated. That can be done throughout, but the problem is that I have tested this model also yesterday, but I could not find a convincing answer to the final version. That means this model, this data that I'm using in SEM4, it will not give us the final answer to that. It's not a tested Excel file. That's what I'm saying. So that's why, because it's not tested, so we may get some result, but that result may not be significant in nature. So there lies the problem over here. So with these limitations, let me proceed further and moving ahead with the concept of this SEM analysis over here. So what happens this SEM analysis, if you can see this Excel file, there are almost 9022. There are 9022 elements over here. If you go down to the Excel file, and it gives rise to something called x1, x2, x3, x4, and there are 13 variables over here. So initial 10 variables, they have some type of nature, and then these x11 to x13, 13, they have some another versions of it. So what happens, what we are going to do over here is that, just give me a minute, please. Okay, this is not relevant anyway. Okay. So this is what the STATA, what you call the first version looks like. If you just click on the STATA, this will be opening up. In your the version that I have shared with you, or maybe through Madam Subhana Madam. So it might have a different licensing component, and this has a different licensing component. That is not important right now. So what we need to do, once we open this data file, so what happens? We need to import the data. So there are different ways of importing data to STATA. So there is a concept of data editor over here. If you see file, edit, data, graphics, statistics, etc. In the second line, there are similar versions of it. So there is a, if you just put your cursor over here, there is a concept of data editor. So if you just click on this data editor, so a open blank sheet like an Excel file comes, right? So what I am going to do, I am going to Excel file this SEM1 model. So what we have to do, I am going to copy the entire versions of it, Control A plus Control C. So I copied this entire versions of it, copied it, and then I am going to this data editor and right click on this. Then there is a concept of copy, paste, paste special, etc. I am going for paste. So once we are going for paste, the first row on the clipboard contains values that can be used as valid variable names. So I just go for variable names by default. I click on it. Okay, there's a problem over here. Just a minute.
Excuse me, sir. Is it possible to take a break right now? The participants are requesting for a 5 or a 10-minute break, if that's fine.
Okay, no problem. In between, I can sort out this problem. Yes, yes, no problem. So we'll meet
All
after
right, sir.
5 minutes. No problem. Okay.
Sure, sir. Thank you.
Okay.
And sir, can I make a request?
Yes.
Hello. Can we get this Excel file on which you're working so that we can do hands-on by ourselves while doing?
Yes, ma'am. I'll be sharing with you, or
Okay.
maybe here only.
Okay. Thanks.
should we start now?
Yes, sir.
Okay.
Yes, I think the participants are joined. We can start.
Okay. Okay, so welcome back. So now, anyway, the Excel file I have
Shall I have
shared.
forwarded the file to the participants?
Okay. Okay, thank you.
Uh,
So, okay, fine. There is another way also, instead of going to that MS Excel file, which will be also the same database, there is another version of using this STATA command, which is mentioned over here. So if you have a STATA command, it's fine. Otherwise, the Excel file which is given to you, that you can also handle. Better is use this command. There is a portions over here. So what happens? There are certain data files which are available uh, in the online mode. So you can access it and use them so that there will be no problem from the data filtration point of view. So just try to write this use HTTP, the usual versions. Then there is a concept of www.stata-trace.com, and then front slash DATA. Then there is a concept of, there is a author, DAC uh, MUSR, MUSR slash NLSY97CFA dot DTF. See, if you just write it and press enter, so you will be getting the same data that you are trying to import it from the Excel file. Now there will be no problem. Basically, there the red sign in the STATA, it has some error component. So that's why instead of going from the SL, but that is not the usual case. This particular data needs some filtrations, and this MS Excel, this using command called use http startuprace.com. Is it visible? Should I make it more larger font?
Yes, sir. Kindly make it larger.
There is no such a format is not mentioning over here somehow. Is there any shortcut key for that? Control plus or something like that? I don't think it is moving forward. The font size is actually not increasing. Okay, fine. So let us proceed further because we have already do not have sufficient time now. So this is the command versions over here. This use HTTP dot thing over here. Anyway, I'll be sharing with you in the chat box if you are using the STATA command file over here. Let me go to the chat box over here and paste over here. So I have already shared with you this link over here. So if you are finding any problem, just copy it to the STATA command versions over here in these portions and press enter. So what happened over here? You will be getting all the requisite data over here. And then just to get an idea that what does it data all about. So just write something called code book, then slash x12 x10, and then something called compact. So this is the nature of the data that we are going to refer right now. So this particular code is not that much important. We are not going to use it subsequently, just to get an idea that what does it indicate. So for that, if you go back to our PPT and try to understand that there is a historical, there is a background of this particular story of the data. So the background of the data, something like this, we'll do the data analysis using the actual data from the National Longitudinal Survey of Youth 1997. And that's why you can see that in abbreviation, it is written as NLSY 97. So this is a longitudinal study that focuses on the transition from youth to adulthood. In 2006, when the participants were in their 20s, the NLSY 97 asked a series of questions about the government being proactive in promoting well-being. So government's role in the welfare measures. So the questions covered such topics as providing a decent housing, college aid, reducing the income differential, healthcare, and providing jobs. So for that, if you want to get an idea in this data file, you can see that government responsibility provide jobs in 2006. Government responsibility keep prices under control 2006. Government responsibility healthcare for the sick people in 2006. Anyway, all those are 2006 reference period. And government's responsibility for providing the indoor help, something like that, provide unemployment and living standard. So these are certain things which is asked to people around, there are almost 9,000 questionnaire, I mean, how persons are asked. So what happens, the questions covered such as, these are the topics covered, and we are interested in using 10 items to create a measure of conservatism. So what is our objective? Because our starting approach is factor analysis. So before going to do that, we want to get some number called some variable called conservatism. Conservatism from the NLSI data. So these data, these items are named as something like this. For simplicity, we have renamed them as X1 to X10. So as you can see below, the responses ranges from 1 to 4. 1 is meaning the task definitely or should be the role of the government, and to 4 meaning the task definitely or should not be the role of the government. So if you can see from the STATA file over here, the minimum and the maximum value seems to be 1 to 4. That means 1, 2, 3, 4, there are 4 scalings they are used. 1 is representing for something and 4 is representing for something. That representations is mentioned over here. That 1 is representing that the task definitely be the role of the government. Definitely be the role of the government is 1, and 2 is should be the role of the government. 3 and 4 represents the definitely not the role of the government, and 3 is should not be the role of the government. So these are the 4 way of measuring it. Higher the scores indicate the person is more conservative. So if it is 4, then any role is not actually meant for. This is not coming under definitely not the role of the government. And if it is 1, then it is definitely the role of the government. If it is 2, then it should be the role of the government. If it is 3, then it should not be the role of the government. This is the in nutshell the background of the story, and on that basis a particular survey is conducted. And as you can see in the data editor file, if you click on the data editor file, it is covering almost 9,000 more than 9,000 responses. 9022 responses are conducted, and its serial number is coming around to 8985. Anyway, it is more than 8,000 people are surveyed and so on. So this is in nutshell the database. So what is our objective is that there are 10 outcomes are there, though this particular file is actually covering 13 variables, I guess. But out of 13, the first 10 we are focusing on, and our objective is to find out something called there should be a what you call a factor analysis should be done. That means the idea behind this particular model is that if you just click on it and move for a little bit further, there should be an idea that there is a conservative kind of latent variable should be generated by taking x1, x2, x3 up to x10. Why it is x9, I will tell you. I will tell you the story right now. But this is the background for that. Is it okay?
Excuse me, sir. The
Yes.
participants are sharing some of the screenshots. If you can have a look at them, they are facing certain problems.
There may be some technical problem. See, what I have, as I have already told you, that if you are not executing it right now, there will be a second session which will be covering all those things, right? So technical things, how to import the data, how to filtering data, etc. So if you are not, I mean, right now, if you are not doing it, or if you are not in a position to do it, just follow them as it is, and then try to do it in the 2 to 5 session where you will be finding more time. That's what I can say, because if I will fix the technical components right now, then it will be not possible to cover the the entire lecture. So that is my concern. So let us see. Anyway, whatever the results are there, I have already demonstrated it over here, and I'll also demonstrate it with the help of the STATA command also. So if you are not executing it right now, just follow the story. Try to understand that what happens if this command executes, then what happens. If that particular results pops in, then what will be its meaning? And if such meanings are there, then how to interpret the results and so on. So individually, each candidate-wise technical solutions will be not possible right now, because we do not have sufficient time. It is already 11:50. Is it okay? And anyway, if there is a problem in STATA, in the R file, that will also be conducted in the second session. So all those problems can be better way handled, because R can be used, I guess, by all of you. And 2 of my students also, they will help you to do that analysis. So that will be, that can be handled better. Is it okay? Should I proceed?
Yes, sir.
So, given that background of the story, so now what happens? There are certain things, and there are 4 outcomes we are getting, like the 4 outcomes I have shown over here. So 10 factors need to be clubbed them together under one, what you call one variable needs to be generated. So what is the procedure to do that? Because we have to do a factor analysis, so I am using a usual principal component analysis. So for that, command is factor, and you have to write x1 to x10, then put a comma, and then write PCF. PCF stands for the principal component factor analysis. So this is the command for executing the factor analysis for taking all the 10 variables together. Till now, I have just tried not put enter. Now, once typing it, if I put enter over here, what happens? We are getting some results like this. And those results are also demonstrated over here. If you can see, this is the command called factor x1 to x10, comma PCF. Then the observations is reduced to 1617. Why? Because there are more or less 8,000 plus numbers are there. Many numbers are missing. So because there is no specifications mentioned over here, so accordingly those missing numbers are gradually deleted from the database, and only focus on 1617 or respondents where all the 10 numbers are found to be present. So that is the objective over here. And when it is when there will be some modifications, like instead of going for 10, if we are going for 9, why? So I will tell you the reason. then what happens over here? The observations are somehow increased, because for all the 10, there should not be any response missing. And over here, for all the 9, there should not be any response missing. And that's why, because the constraint is relatively less over here for all the 9, the observations increases, whereas the previously observation was 1617 only. Now, whatever the result we are getting over here, if you want to try to club them, and if you are trying to find them, that whether you are getting the same result or not, so you can get the eigenvalue, it is over 3.91. The factor 2 is 1.01, and these are the factors loadings over here, 0.60464, 0.5810, and so on. So in the PPT file also, you will get the same result over here. Now, what the problem arises over here, if there is a analysis over here, no, there is no such analysis. So now the problem over here in this principal component factor analysis is that there we are getting 2 eigenvalues, and technically speaking, if any eigenvalue is more than 1, then accordingly that should be considered to be the most the principal factor. That means there should be a 1 factor which will be taking into consideration, and these are the factor loadings. These are the factor loadings combined with that, it will give rise to a latent variable, maybe conservatism or something like that. That is the idea behind the principal component factor analysis. Now the problem in this taking all the 10 variables, what happens over here? That means there are getting 2 factors over here, because factor 2 is also 1.01, and this 1.01 is also technically speaking more than 1, and there is a possibility of something called 3.91, which is definitely the case. So because there are multiple factors and multiple variables are coming over here, so for the sake of simplicity, what we can do, that if you can drop some of the variables, and what should be the approach of dropping the variable? Because if you can see the eigenvalues, subsequently the lowest factor 10 over here, or in other words the extent, these factors loadings, if you focus, these factor loadings are, the lowest value is something called 0.4543, and the highest value is coming around to be something called 0.7221. So that means 72% of the x3 variable, 45% of the extent variable should be represented in the factor which will be covering all the 10 variables. So now what happens over here, there is a problem with respect to this particular factor loading, and technically speaking, if any factor is less than 50%, then that should be 0.5. Any factor 1 loading over here, if it is less than 0.5, then that particular variable should be dropped from the system. And that's why instead of taking 10 variables over here, we are redoing this exercise for x1 to x9. Why we are dropping x10? Because x10's factor loading is less than 0.5, and it is 0.4543. That means in the overall factor, whatever may be the name, conservatism or any other name, if you want to give it, then its AR will be less than 50%. Technically, it should be 50 or more than 50%. And that's why we'll be dropping them, and we'll be redoing this exercise. If you go to the STATA file over here, and if you redo this exercise, factor x1 to x10, instead of x10, if you just write x1 to x9 and do this PCF analysis, you will get the result which is demonstrated over here in this right hand side portions of the PPT. If I just make it full size, you can say that the same factor x1 to x9 PCF. And now if you can see the relative factor loading over here, none of them is less than 0.5. So it will be relatively better model in comparison to this model. Is it clear till now? Out of 10 variables, we are going for a factor analysis. This is the result of the left-hand side. Individually speaking, the factor loading should be 50% or more. What we find that X10 is having a 50% or less loading the capacity. That's why we redo this exercise by dropping the X10th variable. And that's why factor X1 to X9, same model. And now what we are finding that all the 9 variables, they are found to be 50% or more than 50%. Where we are getting 50%? If you just multiply 100 in every one, then it is covering 62.43, 58.83, 72.22, and so on. If you want to cross check whether the same result is obtained or not, it is 62.43, 58.83, 72.22%. Is it clear? So this is the way in which we start with the principal component analysis, but subsequently we have to go to some other type of thing as you will be proceeding further. Why there is a problem? Problem is that if you do this type of analysis by using a principal component analysis, then when we can run PCFA, we hope that there would be a single dominant factor. So with CFA, that means confirmatory factor analysis, then this confirmatory factor analysis, we specify the number of factors. In this example, we specified that the covariance of 9 items is fully explained by the single latent variable plus the unique variance of each item. How do you present it? Just see the conservative, this is the confirmatory factor analysis. In the principal component analysis, only x1, x3 to x9, which is represented over here in this right hand side, they are actually giving rise to a particular variable called conservative. If you go for a predict now, if you do this exercise and go for a predict analysis, you will get a factor component called conservative. But now the problem is that in case of confirmatory factor analysis, not only these 9 variables, they are giving rise to a latent variable. Rather, these error terms, they are also affecting the conservatism. So in other words, there are 2 types of variable. One is this deterministic variable. Another is this unknown variables are called these error terms. So that is the beauty of this confirmatory factor analysis over here. And that's why instead of going for the principal component factor analysis, we are going for a confirmatory factor analysis. So in this confirmatory factor analysis, the covariance of the 9 items is fully explained by the single latent variable plus the unique variance of each item. So this plus unique variance of each item was missed out in case of principal component analysis, which is considered over here. So notice that we are estimating the unique variance of the error variance of each 9 observed indicator here. So that is the idea behind this dropping principal component factor analysis and going for a something called the confirmatory factor analysis. And now if you go for a confirmatory factor analysis over here, then how to do this thing? So you have to use this SEM command. This SEM command is the structural equation modeling command. Now you have to specify what should be the name of that latent variable that you want to generate. So in that case, you just write any name. Ideally, by following that particular procedure, we are writing conservative. And remember, this conservative should have a capital name. It should not be small name. If you just try to with the smaller version of the conservative and do this approach, then that may not be the appropriate way. So what we are going to do over here, that once principal component factor analysis failed over here, so the next thing is that you have to go for something called confirmatory factor analysis, and that command should be like this. It should be SEM, give a space, then start the bracket, give the name of the variable conservative, and the capital, it should be started with a capital sign. Then you have to give a space, then this command like over here. So you have to give a arrow kind of mark. Conservative is giving rise to something called x1 to x9, and then put the bracket close. So this should be the command over here. SEM means structural equation modeling. Obviously, this is not the overall structural equation modeling. It is just giving rise to a conservative latent variable that will be covering x to x9. And if you just after this thing, if you just put a enter command over here, so the results are coming like this. So these results, if you see this result, and if you go back to the slides results over here, the same result you are getting. Only thing is that I represented it in 2 parts. One part of the story is this x9 up to x8 over here, and from x9 and this component over here. If you want to get a clarifications over here, then you can see that this is the command measurement into exogenous variable. The latent variable is the conservative. It is going for certain type of iterations and so on. Now it is a time for doing this interpretation that whatever we are getting this result, what does it indicate? Because this is not the previous type of factor analysis like the normal eigenvalue related kind of stuff. Rather, it gives us something different. And what does it indicate? That is the analysis over here. So what we can find that the CFA is adding value to the principal component analysis. While in the PCFA we assumed conservatism had to explain all the variance among the 9 items. Here we acknowledge that each item may have some unique variance that we are treating as random error. We assume the error variables are normally distributed with mean of 0. This is the assumptions of the principal component factor analysis. There are real advantages to the confirmatory factor analysis. By isolating the shared variance of 9 questions from their unique variances, we are able to obtain a better measure of the latent variable. We are also likely to get stronger results by removing measurement error if the latent variable is subsequently used as an independent or dependent variable in the structural equation model. This is because measurement error by its nature only adds noise to the measure and has no explanatory role. So that is the beauty. The only difference is that if you focus, only these 9 items were there in the principal, but the confirmatory factor analysis along with these 9, all the 9 error terms are also considered. That is the fundamental value addition of the CFA in over and above the what you call this 3. Now, this is the versions that we have done over here. This is for the what you call unstandardized model, the left hand side and the residual part of it. So, if you want to get a standardized version, then this is the standardized versions of the result. I will tell you what is the difference between unstandardized and standardized. But just first go to the unstandardized component that we have seen over here. This is the command because we have not mentioned anything called the standardized versions over here. So that's why whatever he is getting result by default it is unstandardized. So whatever is the residual, sorry, not this one, this one. Whatever we are getting over here is nothing but the unstandardized result. How do you interpret this unstandardized result? So what happens over here at the top of the results, we see that we have 7360 observations with missing values excluded. Just line by line, I want to narrate the story over here because the example is just before here. So here, what happens over here? The number of observations is 1625. Sorry, not this is standardized. The previous one. So 7360 observations with missing values excluded, and that's why some number called 1625 numbers comes. And then the deferred estimation method, maximum likelihood method is used. It uses list-wise deletion and drops any observations that do not have a response of all 9 of our items. For the results next report our endogenous dependent variable. Notice that list-wise deletion, we only have 1625 observations that have no missing values. All of our observed items x1 to x9 are endogenous. That is, the measurement variables depend on the latent variable. So if you go to the find over here, so endogenous variables is the latent variable called conservative, and endogenous variables are the measurement variables or something called what we call it as a measurement variable, the observed variable. The measurement is nothing but the observed. The same terminology used in STATA called measurement that we have seen previously as the ordered variable, observed variable. So these measured or observed variables are 9 and the latent variables are conservative 1. STATA does not list the measurement error terms to here, even though these are also latent exogenous variable. The results above include the sections labeled called measurement and a section reporting the variances. If you see over here, these sections is something called the measurement section. It is written measurement up to x9, and there after there is a bar. These particular items we call it as a variance reporting sections reporting variances. The measurement section gives estimates of the unstandardized measurement coefficients at the loading and their standard errors and a test of each estimate along with a 95% confidence interval. So if you go back over here, what we can see that the conservative over here, excluding the first component, the conservative component over here 0.7377 is significant. Conservative 2x3 is also affecting by 0.8267, which is also significant. So all those components called 0.73, 0.82, not the constant term, only the coefficient term. So 0.73 is statistically significant, 0.82 is statistically significant, 0.75 is statistically significant, 0.75 says that the conservative latent variable is covering the determinant from the X4 component by 75.55%. Similarly, the conservative latent variable from this X5, or in other words, X5 is affecting conservative latent variable by something called 73.8% and so on. So this is the way in which we can understand that these are all factor loadings over here. So this is the interpretations over here. So factor loadings and the standards and a test for each estimate with a 95% confidence interval also there. STATA fixes the loading of the first indicator at 1. If you focus on the unstandardized version, the first component coefficient is found to be 1 and it is called as constraint. It has a meaning also. What does it say? That it fixes the loading of the first indicator at 1. The indicator that has its loading fixed at 1 is called the reference indicator. All the unstandardized estimates will change if the change of the reference indicator changes. So it is a good idea to have one of the stronger indicators be the reference indicator. If you want to change the reference indicator, then you have to just change the command, because it starts from conservatives in x1 to x9. Because the variable x1 is written first, that's why the x1 is considered to be the reference indicator. If you write with x2 to x9 and then x1, that means x2 will be the first reference indicator, and then accordingly the number will be changing also. But the significance level will not significantly affected because they are partial econometric analysis. So that's why the significance level will not change. But for the sake of your own convenience, if you want to check that instead of going for x1, then you just write it as x2 to x9, then space x1. That means x1 will also be there, but x1 will come at the end and x2 will be considered to be the reference indicator. So that is the idea which is represented over here. Now what happens over here? With exploratory factor analysis, we usually focus on the standardized submission. This standardizes all variables, both observed and latent, and have variance called 1. So what happens over here? This the slide that I am deliberately skipping for the last couple of minutes. Now this is the meaning over here, that once you do the unstandardized version, like over here, if you go for the STATA over here, after conducting these unstandardized versions, if you just run something called SEM, then put a comma over here and then give a space and write standardized. Just write standardized. SEM, put a comma, space, standardized. Then you will get the result which is mentioned over here. The same result which is mentioned here. This is the unstandardized version and this is the standardized versions over here. So in the standardized version, what happens over here? The variance of the conservative is found to be 1, which is not the case previously. The variance of the conservative thing, it was different from 1. Because in the standardized version, we are assuming that it is 1, that's why the result is coming. And whatever we are getting in this result after standardization, whatever is the outcome, we call it as an exploratory factor analysis. Before standardization, whatever we are getting, that is the normal confirmatory factor analysis. Technically speaking, that is the only difference between the two types of approach called confirmatory and exploratory. The exploratory will be useful for us to do the interpretation, but that does not necessarily mean that confirmatory analysis is meaningless. So that's why there is a necessity of both confirmatory and exploratory factor analysis thing. But whenever we are analyzing SEM standardized, the corresponding result is nothing but the result of exploratory factor analysis, and whatever the result before it, I mean without doing the standardization, this result is something called the confirmatory factor analysis. I think it is clear till now. Is it clear? I
Yes,
understand
sir.
that if you can execute on your own, it will give you more value addition. But because of some technical problem, I cannot help you out currently. It needs little bit, at least 1 week time to get to know all the things in a very proper and coherent manner. Within 3 hours, it will be very difficult. Anyway, the analysis part we have just started. I am very skeptic that whether we can able to finish it within half an hour or not. So anyway, let us proceed. What I am asking that is there any thing needs to be told you once more time, or it is fine? Instead of going for writing in the chat, if you can tell me on my face, then that will be more useful, because I cannot go to the chat box and read your comment. Or maybe the moderator can help me in this regard. Any doubt till now?
So I think we are good to go. It's fine.
Okay, so this interpretation of the CFA result we just finished over here. Now, after doing this exercise, we do one component and we do some variables we generated over here. These are all the factor loadings, and as usual, we know how to do these conservative variables are generated. So in the similar manner, we can do it. But after doing all those exercise, whether this confirmatory or exploratory analysis that we did for all the 9 variables generating something called latent variable called conservative, whether it is reliable or it cannot be reliable. So for that, what we need to do, we do a reliability test. This is the starting point of the diagnostic checks. So in the reliability test, what happens, we are using a CFA model, obviously / EFA model also, exploratory factor analysis. We can estimate the reliability, which refers to the proportion of the total variables in the scale formed by our indicators that is attributed to the true score. If you obtain a high reliability estimate, say 0.80, then this means that our true score can account for 80% of the variation in the scale we are using. The latent variable in the CFA is intended to represent the true score and be free of any measurement error. So how to do that? So there is a formula for that. We call it as a rho for the confirmatory factor analysis. It depends on a ratio. The numerator is summation lambda I square. This lambda I is nothing but the unstandardized loading. If you go back to the previous slide, unstandardized. So whatever we are getting this unstandardized loading on 0.73, 0.82, 0.75, these are called lambda I. So these lambda I's are getting to be square. That means find out sum total of all those lambda I. So sum total of all lambda I means 0.737 plus 0.826 plus 0.755 plus 0.738 plus 0.914 and so on up to 0.927, because these are the all factor loading lambda I. So these lambda I needs to be sum total. Just add them and get a square term, which is the numerator. In the denominator, the same value will come along with two other. The two other is theta II. The theta II is nothing but the sum of the unstandardized error covariances. So what is that error variances in the unstandardized variance? These are all unstandardized error variances. This is the unstandardized model. So this is the error variances. So what we need to do? 0.72 plus 0.47 plus 0.23 plus 0.21, add them together. That will give rise to something called the theta IA. And then plus theta IJ. Theta IJ represents the 2 times sum of the unstandardized covariances. 2 types of unstandardized covariance means in the previous model, what happens over here? The EX1 and EX2 covariance is not considered. That means this error term and this error term is assumed to be not correlated. This error term or epsilon 2 and epsilon 2, they are assumed to be not correlated. And on that assumption, this model is built. If you assume them, then accordingly, they will be reflected over here. And that reflection will be represented over here. And that is nothing but theta IJ. That means if it is theta 1, 2, that means epsilon 1 and epsilon 2, they are correlated, and find out its covariance. It will come over here. And if epsilon 2 and epsilon 2 and 3 are correlated, if you assume in the model building, then accordingly it will be reflected over here. And those components are called theta IJ over here. And we are finding out its sum total and just 2. In this case, in the current state, this theta ij is found to be missing because we are not assuming in our model building, we are not considering that. So that's why because theta ij, not a single theta ij is there. So sum total of theta ij is also 0, and 2 times of theta ij, sum total of theta ij is also dropped out. That's why this entire model is limited to the summation lambda I square divided by the summation lambda I square plus theta I. So what happens over here? The way in which we are generating over here, if you just put it the summation lambda I square, whatever is the summation, the same number and this. So obviously the numerator and the denominator may be same, may not be same. If this theta I summation is found to be 0, and remember what does it mean? All these variances, if they are found to be 0, so the sum total of theta I will be 0, and then only the reliability will be 1. Obviously, these error terms have certain variances and they will be reflected over here, and that necessarily indicates that this particular theta I will be non-positive, non-zero. Hello? Is it too technical? Should I skip it?
No, sir, it's fine.
Okay. So what I'm trying to say is that the numerator and the denominator may be same only if we are only in the case that theta I is 0. If theta I is non-zero, and that will be the usual case non-zero, it cannot be happen that it will be 0, and that's why, because any variable will be in the denominator, so denominator will be higher and numerator will be less. But the only thing is that the entire exercise will be reliable if this numerator to denominator ratio is found to be 0.8 or more. If it is 0.8 or more, then rho is 0.8 or more, indicates that it is a reliable. If it is not, then it cannot be reliable. So you try on your own. This is an exercise for you. Find out all these 0.73, 0.82, add them, square them, and this is numerator. And this add them, so square them, and over here 0.72, 0.47, add them and square them. What you will find that your rho value is coming around to be 0.80 or maybe 0.81. I'm not sure. So that's why on that basis we can conclude that this confirmatory factor analysis is reliable only from one indicator point of view. That is, from the reliability test point of view, the CFA result is not bad because the rho is found to be 0.8 or more than 0.8. But it is not tested. Manually you can do it. There is other way also can be done, but I'm not going to that part. So it is the case that this is one check post that reliable or not reliable. Then the thing is that what are the other goodness of it that we have discussed in the previous model. So what is the other goodness of it? So for that, this part and this part needs to be discussed. So what we can do, we can go back to our previous case. So what is the next model is that because the reliability test it passed, then let us go for E start. GOF stands for goodness of fit, comma, and then you write stars within bracket all. So this is the command for assessing the goodness of it. So if you enter it, you will get all those results over here, and these results are nothing but represented over here in these left hand portions. So try to understand what happens over here. These are the things that we are discussing in our previous slides earlier. So these are the likelihood ratio which comes in the chi-square test format, chi-square statistics format. So this chi-square statistics has two chi-square. One is a chi-square MS. As you can see that MS is the measurement related thing. If you recall, there are different versions earlier, as we have mentioned. If you recall, something called the saturated model is something called MS. This BES model is the baseline model, and this SM model is something called the specified model. So these are the results we are getting over here in these portions. So what we are getting, this saturated model is coming around to be 419.007. So model versus saturated, this is the comparison, and it is found to be significant. Then there is a baseline which is coming around to be 3872, and this baseline versus saturated. So how do you compare them? That for the likelihood ratio, in the first one, anyway, both of them needs to be significant, and the first one definitely should be significant. If it is significant, then it is says that the goodness of it in terms of chi-square test portions, the model is relatively good. And similarly, that can be seen with respect to other component. If you recall now that what is the criteria for RMSEA, what is the criteria for the CFI, what is the criteria for TLI. The CFI and TLI criteria was if it is 0.95 or more. So in that case, it is not found to be significant one. It is less than 0.95. And similarly, the SRMR, it should be how much it should be? It should be less than or equal to 0.06, I guess. Anyway, we can revisit to our analysis over here. SRMR should be less than 0.08. Your TLI should be greater than 0.95. CFI greater than 0.95. Your RMSEA should be less than 0.05 or 0.06. These are the parameters over here. So what happens over here? You can see that in the result segment, over here, we can find that some of them are found to be significant, but not all of them. That means your chi-square is significant. Your RMSEA is found to be 0.095, which is not significant because it should be 0.05 to 0.08 kind of stuff. It is almost crossing 10%. It is almost 0.1 category, 0.095. So if there is a lower and upper limit for that, but still then it is not found to be significant. CFI is not significant because it should be 0.95, but it is not. So these number indicators that this exercise is not a futile exercise, fruitful, but still then there is a lot of things need to be improved in the model. That is the indication given by the analysis up to this. But now the STATA can give you some hints that what may be the possible scenario for scope for modifications. So for that scope of modifications, what we can do, we have to use this command called, there is a concept called the MI. MI stands for something called modifications indices, and for that we have to write something called ESTAT and MINDICES. M indices. You have to write that called ESTAT M indices, and you just enter it. You will get some result called this ESTAT M indices result. And if you see this ESTAT M indices results, it is the same result which is mentioned over here. The same thing. Now it has a more story to narrate. What does it say? That if you go to how to modify the model and what is its guideline. So far the confirmatory factor analysis result is telling us that our model is not ideal. The reasons I have told you earlier, because RMSEA is not a good model, and I mean for CFI TLI is also not greater than 0.95 and so on. So but the result does not indicate what we might change about our model. Till now, M indices, without M indices, it cannot give us any scope for improvement. A modification index is an estimate of how much the chi-squared will be reduced if we estimated a particular extra parameter. For example, our model might be fit better if we correlated the error terms for a particular pair of variables. So each parameter we might add uses 1 degree of freedom. A chi-square with 1 degree of freedom equal to 3.84 significance at the 0.05 level. Therefore, for each modification index is bigger than 3.84, we would significantly improve a fit model by reducing the chi-square significance. So what we can see that these are all possibilities of inclusion. That means if you can include in the initial model, where the initial model was only this much, that means you have to generate a conservative by taking x1 to x9 only. This is the original in the original model. So what they are suggesting that if you can include error term of x1 and error term of x2 covariance in the initial model, then that can be add value. And there are several other things are there. So from that, one after another, there you cannot go for doing this exercise for infinity period. So what best you can see that whatever is the highest among them, it will give you an indication that that can be brought into the model, in the initial model. So that means the error term of x3 is not the x3 and x4. It is the error term of the x3 and x4 model. That means in the previous thing, the error term of epsilon 3 and epsilon 4, they needs to be correlated because their covariance is very high, and that's why it cannot be ignored in the initial model. So that's why what we need to do, that in the modified model, what we have to do, we have to take into consideration the covariance of x3 and ex4 also into the picture. But again, if you do that, then also there may not be an appropriate model. There can be some further thing. So that further thing is removed over here. So what we can do, we have to again go back to our previous literature and logic. That maybe all the 9 variables, they are very large in number. If somehow we can reduce the number to 7, 6, or 8 or whatever, then that can be a better way. But how to do that? You have to do this exercise by saying that the modification should be substantial and it can be theoretically justified. So obviously, nobody can give you the guideline that which model should be dropped, which variable should be dropped, or what happens to the other variable, etc. So it is completely on the basis of your trial and error mechanism. Drop x4, drop x5, drop x3, drop x2, and so on. Ultimately, what we can do, that because this is a tested model earlier, so we can re-examine the model by taking only the x3, x4 error variance. It is not possible. So what we can do, the model is still weak to fit the data. This makes us wonder if one or more of the items really should be dropped because they're problematic. So we'll drop the 2 variables called x2 and xt. Again, this is not the random one. This is on the basis of trial and error. Drop x1, keep other variables. Rerun the exercise, find out all the diagnostic checks. Run the model by dropping x2. Run the model by dropping x3, and whenever you will do this exercise, it should be one at a time, not that at all the point of time you drop 3 and then include 2 and so on. So it is a hectic exercise, and that's why when we are discussing its limitations, it is a complex exercise. Now you can understand what is the complexity over here, and these keep the variance error term over here. So what is indicating that you have to run the model again. The same conservative thing, which will be path is going from x1 to x9. But now what happens, it is not x1 to x9, rather x1, x3 to x7, drop x8 and take x9. That means x2 and x8 is not there. And this comes after a lot of exercise, which is not mentioned right now. It is completely up to the researcher to do this exercise on their own. So drop x2, run the exercise, drop x8, run the exercise, drop both x2 and x8 and drop the exercise, run the exercise. And then in addition to that, covariance. And covariance of x3 and x4, they are interrelated with each other. So that's why they are multiplied with each other. And where does it come from? It comes from these M indices, because error term of x3 and error term of x4, they are very highly correlated. So that's why the covariance should also be modeled in the system. So that's why the covariance is modeled. So how to do this exercise? Again, we have to go to our previous model. So what we do, a lot of things need to be done over here. SEM, then something called conservative, then give a space. This is the path. Then you write x1, give a space, x3 to x7, because x2 is dropped. Then give a space, x9, put the bracket. These are all with respect to the measurement part. Then put a comma. Then you write something called the covariance. Covariance of something called error term of x3. Error term of x3 needs to be multiplied with. So put a asterisk mark for that. Error term of x4. And then put a comma, bracketed. So this covariance thing needs to be within a bracket, and this conservative thing will be another bracket. So SEM conservative x1 to x9 by dropping x2 and x8. Then covariance of it, EX3 multiplied with EX4. If you do this exercise, okay, I'm sorry. This command needs to be EX3 and EX4. It's better if you just copy it from here. It should be paste over here. EX3 instead of comma, you just write asterisk mark. So this is the command now, EX3, EX4, and then enter. So this is the result we are getting. So remember what happens over here in this model. In the previous model, only conservative to x1 to x9. Now you drop two variable and add covariance of ex3 to x4. So this is the new model which is mentioned over here in this slide. So this is the new model. Initial model is remodeled over here, and this is the result of here. And if you go for again E start QOF start solve, that means if you want to go for the goodness of fit model, then this is the new model, and this is the new goodness of fit. So new goodness of fit says that the chi-square model is found to be significant. Previously, the chi-square model is 419, so it is reduced to 6.0291 because earlier the two variables are dropped and one covariance term is added. So ultimately, it is going to affect the chi-square model. But what happens over here? The root mean square error, which is found to be earlier greater than 0.095, now it is found to be 0.045. And accordingly, the baseline comparison like CFI and TLI is also greater than 0.95. SRMR is less than 0.06, 0.021. So on that basis, the model is found to be relatively more parsimonious in comparison to the earlier model. But this result comes with a lot of patience and adding and dropping several things into mind. So software will help you, but it cannot replace whatever your common sense and logical computation is there. So that is the beauty. And now you can understand the comparison between AIC and this BIC with the previous. Now this is model 2. Now the AIC, BIC make a sense. Previously, we are not interpreting AIC, BIC. Whatever the number, we skip it because that is the only model. So there is no point in making a comparison. But this is the diagnostic test of the model 1, where the AIC is found to be 31,241. Whereas this is the model 2, whereas the AIC is found to be 25,312. Indicating that this exercise is relatively a better exercise in comparison to the exercise which was conducted earlier, this exercise. So that's why we have to generate a conservative mechanism like this, but along with a modifications. And that modifications gives rise to something like this. This gives rise to something like this, where the conservative is the model which is generated from x1, x3, x4, x5, x6, x7, x9. x1 was previously dropped from the principal component. x2, x8 is dropped through our model modification, and x3, x4 error terms are modified. So compare between this modified model along with the previous model, which was the earlier model like this. This was the initial model. So that's why this is the initial confirmatory factor analysis, which is modified to this new confirmatory factor analysis like over here. And this is the final results of the confirmatory factor analysis. This is the model of unstandardized value. And if you go for a standardized value, this is the exploratory factor analysis. So these are the different factor loadings. That means we can say that X1 is contributing to the conservative 56%, X3 variable is contributing 58%, and so on. These are the standardized value which are the reference point for comparison. That means X1 is relatively contributing less, though minor less, in comparison to X3, because 0.56 is less than 0.58. 0.56 and 0.56 are same. So that means X1 and X4's contribution to conservative will be more or less similar, whereas that comparison cannot be considered from the unstandardized value point of view. So this is in nutshell, the conservative family picture comes over here. Is it clear?
Yes, sir.
See, I
Okay.
is
So this
participants
is
please respond.
okay. So this is part one of the story. Within 5 minutes is never possible. So let me try to wind up the discussion because this is the way in which you have to do. This is part one of the story. If you recall, this is data analysis one, which is with respect to confirmatory factor analysis. Now, the confirmatory factor analysis can be two types. One is one factor model, another is two factor model. Again, I'm going to skip it because in the initial model there are 13 variables. If you recall, if you recall, there are 13 variables over here for your I mean confirmation. Let me go back over here. So we are taking compared to 10 over here. But if you go to the data editor files are up to x13. So there are 13 variables over here. So that's why what happens over here, we are taking only 10 variables and do the exercise. But what happens, the other three variables, they may give rise to some other type of latent variable. So like x11, x12 and x13, they may give rise to something called a depression latent variable. And that depression latent variable may be interrelated to conservatism. So accordingly, this is the what you call the confirmatory factor analysis for the part 2. This is the confirmatory factor analysis that we have recently done, part 1, and they may be interrelated with each other. So that is the advancement of the two-factor model, and the corresponding procedure will be same. So you start with the generating a depress x1, x13, taking the variable. Then we'll be redoing this exercise that you have to do the structural equation modeling, where the depress is the depending on three variable. Conservative is depending on the x1, 2, x3, x7, x9, and covariance. So taking them together, you will get the entire model. So this is the two-factor model, where the two-factor model x11, x12, x13, they are going for depress. x1 to x9, they are going for conservative, and accordingly the variance covariance portions is mentioned. And then you have to go for the same procedure called goodness of fit analysis, estimation of modification indices, and then find out the cases. Now the case indicates that there is a possibility of error term of x4 and x5 may be interrelated. Go for a modified version, then go for again goodness of fit analysis, and the procedure will continue. That is the end of the confirmatory factor analysis. Now moving to the path analysis, as I have told you, the path analysis is a indication that where does the causal relationship, not exactly the causal relationship, how to make the analysis clear. Because of the paucity of time, I do not want to go into the details. Anyway, I mean it is going to cover the time soon also. So what happens over here for the path analysis, the data background is something like that. This is not related to the previous. Now this is a fresh example where four variables are there. First is related to 2, first is related to 3, first is related to 4. And 2 is related to 4, 3 is related to 4. And this is the way in which we are doing the path analysis. So what we can do, we have to do the similar procedure going for a structural equation model where this math 7, that is what you call the variable 2, is influenced by attention 4. Attention 4 towards math 7. So math 7 is influenced by attention 4, bracket end. Read 7 is another variable which is influenced by attention 4. And this math 21, the last variable, is influenced by attention 4, math 7 and read 7. So attention 4, math 7 and read 7. This is the way in which we can do the path analysis. If you do not write anything and just execute the command, then also the result will come something like this. Some results will come. Otherwise, if you go for some modifications, like the method is usually maximum likelihood. There are other versions of maximum likelihood methods also available. This method called MLFB, it represents that if the missing values are more, and if you go for the standardized versions, this is the model. So this is the way in which we will do the path analysis, find out its statistical significance. The usual analysis will continue, and then you go for all those things. Only difference between this additional thing is that E-stat equation goodness of fit will come, which was not there in case of confirmatory factor analysis. Otherwise, the same procedure that you have to find out goodness of fit, then modification procedure, and there is an equation of goodness of fit and total effect will come. Why total effect? Because the effect on the MAT 21 is not only for attention 4, it is attention force effect via MAT 7 to MAT 21. And similarly, attention force effect via read 7 to MAT 21. So these are indirect effect. This is the direct effect. Similarly, this is the indirect effect. So there are total effect which will be combination of direct effect and indirect effect, and the corresponding analysis will continue. And the results are mentioned over here. The equation of goodness of fit is coming around to be only 0.05. Now you can imagine your R square value is coming around to be 0.05, how robust your result may be. But in comparison to other models, they are also found to be not so significant. Your confirmatory factor, CFI result is 0.95, and this RMSEA is 0.249. So obviously a lot of problem is arising over here. So accordingly, E-stat M indices indicates that there is a possibility of several modifications required, and one modification is considered over here. That means the error term of Math 7's error term, and error term of the read 7's error term, they may be interrelated. So you do the same path analysis like the previous command that we do over here. This is the previous model 1 for the path analysis along with these indications. So it gives rise to something called structural equation modeling, attention 4 to Math 7, attention 4 to read 7, attention 4 Math 7 read 7 to Math 21, and then go for the same along with the covariance and do the same exercise. Now finally what happens, there is a total effect. The total effect has a structural component only, and the structural component is the totally direct effect component, indirect effect component. The direct effect component indicates that attention 4 has a significant effect on Math 7. That means if you remember over here, attention 7 to Math 7, this path is significant, direct effect. Whereas attention 4 to read 7 is also significant. That means attention 4 to this path is also significant. Path 1 is significant, part 2 is significant, and then all the three also contribution to Math 21. So all the three means this part, this Math 7 to 21 and read 7 to 21. These are all the direct effect. Whereas in the indirect effect, the attention 4 to Math 7, indirect path over here is found to be missed out because there is no indirect path. Similarly, there is no indirect path mentioned. Only indirect path is there, which is attention 4 to Math 21 via something, and it is found to be significant. So when direct plus indirect, if you add them together, 0.129 plus something like this, you can generate this number called 0.129 because it is 0. Similarly, this number plus this number gives rise to this, which is also same. Now these two numbers along with 0, they are same. Only thing is that 0.100 with indirect effect 0.06, it found to be 0.16. So this is the effect of the path analysis called the total effect. Now if you plot them together, it will give rise to something called structural equation, where the same model is there, where all those specifications need to be mentioned, and this is the way in which we will do the exercise. I stop over here. I do not know how far I have covered, but these are certain SEM builder component. Graphical exercise need to be done. So I'm sure in the second part, whenever whosoever will be doing this exercise, he or she can be in a better position to complete this assignment. So thank you very much. Any doubt, any query? If you have till now, whatever we little bit discussed, you are most welcome to ask.
Thank you, sir, for the session. So participants are requested to kindly ask their questions or queries.
Sir, can you go to your slide number 73? I missed that part. The last one from, yeah. Okay.
Okay. Yeah, it is not covered till now. If you want to demonstrate it with respect to some number, then I can help you. I can just give you a snapshot for that. So in the STATA version, in the statistics, if you go to structural equation modeling, then there is a model building and estimation. This is the, if you click on that, then something like this will come. And this thing is actually mentioned over here in this case. So this is a STATA's SEM Builder, and there are different components over here, and these different components are just mentioned over here, which you can see from this. These are the things. If you just take your cursor over there, then select. This is add observed variables because it's a rectangle variable. Then it is a add latent variable, which is oval set variable. Then there is a add multi-label latent variable, which is not covered till now. And there is a add path. The path model can be there. So these are the add covariance and so on. So if you want to generate some variable over here, then you can do that. Otherwise, if you there is a portions like here, if you just click over here and mention something like this, it will give you you pop up something, then your measurement variable, like something called x1, x2. Sorry, we have not taken into consideration x2 in the final model. So x3, x4, x5, x6, x7, x8 is not there, x9 is there. So these are all x9, and in this case you just write CONSV, the conserve thing. So your latent variable is conserve, and your measurement variable is x1 to x9, dropping x2 and x8, and these are the things. And if you want to measure the directions, something called up, down, left and right, etc. So this is the region. So suppose down is the region, and if you go for OK, so this is the model that we can see. Can you see this model now?
Yes, sir.
So that is the thing that we are discussing earlier. So this is just a graphical representation of it and nothing else. Okay. So this is the model, and if you want to say that I want to execute this model, so what do? You go to estimation part, and there's just estimate over here. This is one way, or there is something called estimate over here. There is a cursor over here called estimate. So you can click over here. Same model, same window will come. So it will asking you that whether you will go for MLMB, maximum likelihood with missing values. Maximum likelihood is by default. So there is a group, if any. There are various portions are coming. So suppose you want to mention your standard error with respect to OIM, which is the conventional one, and reporting is something called report the p values, display the standardized coefficients, do not report the constant, and so on. And either some model, some changes you can do. So these are all what will be the result which will be coming. So if you do this and go for OK, so these are the results. These are the results that we have obtained earlier also in the previous case for 0.55, 0.67. If you go to your previous slide where you are mentioning that in the confirmatory factor analysis part, this is the 0.56, 56, 58, 0.56 model, which is mentioned over here, and this is the result that we are obtaining over here. This is the 0.55, 0.67. The results are different because this error 3 term and error 4 term should be needed covariance with each other. That we have not done. If you want to do that exercise, suppose you bring this covariance, and this is the which two variables are correlated. Just wait a minute. This is x3 and x4's error terms are correlated. So x3 and x4's correlation, these two things are correlated with each other. So if you add and drop them over here, and so this is the model. This is the modified model. The earlier model was not here. Now you have modified the model, and then if you go for the estimations thing, keeping other things constant, no changes, and then OK, then you are getting this model. 0.56, 0.58, 0.56 is the same result that we have obtained over here in this case. 0.56, 0.58, 0.56. and this is the covariance relationship is 0.38, what we are getting over here, and we are getting the same 0.38 here. Is it clear? That is the exercise that we need to do in a very elaborative manner by taking a proper structural equation model. But somehow, because of the paucity of time, we couldn't do that. But somehow I managed to demonstrate it with respect to SEM Builder now. Is it clear? We did not do any estimation. We do not put any syntax commanding over here, but that does not necessarily mean that this is not resulted. Whatever you did over here in these modifications, you can find it over here. The same. We run the model 2 times. If you recall, in the initial model, we do not go for the covariance, and this is the result over here. And once we go for a covariance term, so covariance terms is added. This is the covariance term, which is not there. So this is the result. So all the results are represented here in this case, and the graphical representations only this case. Just for the sake of simplicity, this is the finding, not cell, and this is the more technical versions that we already get it. Like, I think, is it clear? Yes, some questions by Salini Kesari. Yes, ma'am.
So I have two questions actually. First is that the commands that we are putting in the STATA software, are those commands case sensitive in nature, like capital and small letters?
Yes, yes.
Okay, sir. And so the second question is that like we are using an Excel file for putting in the data in the software. So how do I make a Excel file of my own data? Is it a set format that the software recognizes, or I can make the Excel file and it will automatically recognize my information?
Okay. No, good question. Actually, it depends on what type of variable you are having. I do not know whether just a minute. This is the
Yes, sir.
practice SEM. If you can see the practice SEM, there is no standard guideline for preparing the Excel file. Normal thing is that if you browse any thing, either it is in terms of only with description, no 1, 2, 3 scale is given. Getting it? So this can be also handled by the software. Not all, depending on the nature of the software, STATA can do this, because we have seen already this type of data that we are using here. There is no number over here, only
Yes, sir.
sentences. So that sentence related stuffs also can be taken into consideration by the STATA. Otherwise, if you go to SEM2, the model, so here, whatever may be the questions, maybe for example, suppose you go to a survey for any type of road transportation, or maybe there is a city mall where there is a necessity of building the ground floor as the parking area or something like that. For that, you need certain survey. So all those surveys, they can be scaled from 1 to 5 or 1 to 7, right? So those numbers can also be represented. So all those questions, maybe you asked 11 questions related to a particular dimension, and then you write them depending on their response. They're highly satisfactory, moderately satisfactory. Then 3, 4, 5, the Likert scale kind of thing. Then that can be considered also by the software. There will be no problem for that. Or maybe a data like over here. This is a proper econometrics related estimation procedure, where we have gone for a panel data analysis. Panel data analysis indicates that suppose there are multiple countries are there, multiple countries like Angola, Benin, there are certain sub-Saharan African countries are there, and they have data over a period, that is from 2000 to something called 2018. And then for second country, it has also, that means it is a panel data, pool data. That means cross section along with what you call the time period. That data also can be considered. So far as the software is concerned, it varies from one software to another for sure. But majority of the software, they can handle cross section as well as panel data. For time series, we generally do not go for a structural equation modeling. But again, that will be very brave or very over ambitious statement. I have not seen for that. But majorly for panel as well as for cross section plot together, the data can be handled.
Okay, sir. Thank you, sir.
So
If
if there are no
anybody
more
has
questions,
any,
then we can, yes, we can close the session if there are no further questions.
Okay. Thank you, ma'am. And as I have told you, that two PhD scholars are ready. So from 2 to 5 p.m. they can, assist the participants. And if necessary, then I will also be joining in between if there is a true necessity for that. Otherwise, I'll
Okay,
be
sir.
out.
Okay, sir. So then we will resume the session from